Hey guys, good morning and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, quickly, just let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Quickly, let me know in the chats with the thumbs ups. Good morning guys, good morning. Welcome back, welcome back, welcome back. So quickly, let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Yes, people? Quickly in the chats. Good morning, guys. Good morning. Welcome back. Welcome back. Hello, Anusha. Hello, Kirthana, Simon, Harini, Killer Science, Charmi. Welcome back, guys. So, all good? All good, guys? All right, all right. So, as you all must be knowing, in the last session, if you remember, we discussed the part 1 of the chapter gaseous state of the chapter states of matter. And in this particular session, we are actually going to complete this particular chapter, right? We are going to accomplish our weekly target. The target which I gave you last week, the chapters which I told you we are going to finish in physics, chemistry, and biology. Today, we'll be completing our chemistry portion in this particular session, right? Perfect. And before starting the session, the ones who have not liked the session yet, I would want every one of you to like the session, to share this particular video with everyone, whosoever is preparing for NEET 2024 or even 2025. This particular session is for everyone, right? And at the same time, the ones who have not subscribed to the channel yet, I would want every one of you to subscribe to this channel as well, okay? So quick recap of the things, like what did we discuss in the part 1? In the part 1 of the chapter, we have discussed the gas laws, right? We talked about the ideal gas equation, density form of ideal gas equation. Perfect. We did a lot of questions based on the graphs, based on the ideal gas part. And at the same time, if you remember, we discussed about the Dalton's law of partial pressure as well, okay? So what all things we are going to cover in the today's session? Well, in the today's session, we'll start with the topic effusion, diffusion, right? Again, important topic. Then we'll talk about the Graham's law of effusion. After Graham's law, we'll go to the kinetic theory of the gases, then the Van der Waals gas equation, okay? The real gas part, I mean. Perfect. So are you guys ready for the session then? Say yes or no in the chats, quickly. Say yes or no in the chats, quickly, everyone. Quickly. Quickly, everyone. Yeah? Perfect then. Let's get going. Let's get started, and it will not take us more than 3.5 hours to complete this particular chapter with all the problems, with all the theory, right? So be with me till the end, right? Perfect. The first topic which we are going to discuss now, that's something which you call as effusion, right? So my dear students, how do we define the term effusion over here? Right? The term is effusion. How do we define it first of all? It's a very simple terminology. Let me write its quick definition. So first of all, how do we define the term effusion? Effusion is defined as the escaping out of gas molecules. The escaping out of gas molecules through a hole when the gas is under pressure. When the gas is under pressure. Now, what is meant by this particular statement which we wrote over here? My dear students, imagine that you have got a container. Let's imagine that we have got a container over here, which is closed on all the sides. This container, it's closed on all the sides. Now, what exactly I'm going to do, I'm going to keep some gas molecules in this particular container. I've kept some gas molecules in this container, right? Now, as you know, as far as the property of gas is concerned, these gas molecules will be in continuous random motion, due to which they will be colliding with each other. At the same time, they'll be colliding with the walls of the container as well. So I can categorically say the gas will be having some pressure. The gas is under pressure right now, right? There will be some pressure for this particular gas which is inside the container. Because you know, as far as the property of gas is concerned, the molecules are always in continuous random motion, due to which they'll be colliding with each other. And at the same time, they'll be colliding with the walls of the container as well. So I can say the gas is right now under pressure. Okay. Now, dear students, imagine that a hole got created over here in the container. Imagine that a hole got created in this particular container. This is the small hole which I'm talking about, right? Now, since a hole got created, can I say some of the gas molecules from the container will start to escape, will start to leave the container? Absolutely. Some of the gas molecules will start to leave the container through this particular hole, right? Or in short, I can say the gas molecules, some of the gas molecules are escaping out from the container, right? Through the small hole. First of all, the gas which comes out of the container, this gas from now onwards, I'll be calling it as effused gas. The gas coming out of the container through the hole, I'll be calling this gas as the effused gas. And the phenomenon of escaping out of the gas molecules through the hole when the gas is under pressure, this phenomenon actually is called as effusion. So what is effusion? Escaping out of gas molecules through a hole when the gas is under pressure. Right? That's what you call as effusion. As simple as that. And at the same time, the gas which comes out of the container, that's what you call as effused gas. Right? Perfect. So I hope your first terminology of effusion, the meaning of effusion, is clear to you. Okay? Now, my dear students, after the term effusion, there is something called as diffusion. There is something called as diffusion. How do we define the term diffusion? How do we define the term diffusion? I'll say diffusion is defined as the spontaneous intermixing. The spontaneous intermixing of the effused gas. The spontaneous intermixing of the effused gas with the atmosphere, to form a homogeneous mixture. To form a homogeneous mixture. What do we call this particular term as? We call this particular term as diffusion. We call this particular term as diffusion. The earlier term that was called as effusion. Now let's try to understand what diffusion is all about. My dear students, first of all, this is the effused gas which is coming out of the container, right? The gas which comes out of the container, it spontaneously intermixes with the atmosphere to form a homogeneous mixture. It spontaneously intermixes with the atmosphere to form the homogeneous mixture. And that spontaneous intermixing of the effused gas with the atmosphere to form the homogeneous mixture, that's something which you call as diffusion. You know, since this is the container, apart from this container, what do we have from outside? We have atmosphere from outside, right? And atmosphere contains different gases basically. So the gas which comes out of the container, it spontaneously intermixes with the atmosphere to form a homogeneous mixture. And that spontaneous intermixing of the escaped gas with the atmosphere to form the homogeneous mixture, that's something which we call as diffusion, right? So I hope two terminologies are clear to you. One is effusion, one is diffusion, right? Can I say something like this? Can I say one more point? Can I say effusion is always followed by diffusion? Say yes or no in the chats. Effusion is always followed by diffusion. So first of all, effusion takes place. First of all, the gas leaves the container, and after that, it intermixes with the atmosphere. So first effusion takes place, and once effusion is done, then diffusion takes place. So do remember, effusion is always followed by diffusion. Correct? So I hope the basic terminologies like effusion and diffusion, I hope it's clear to you. So in short, again, if I ask you what effusion is the escaping out of the gas molecules through the hole when the gas is under pressure. Number one. Diffusion, the spontaneous intermixing of the escaped gas with the atmosphere to form the homogeneous mixture, right? And once effusion takes place, right after that, what will happen? Diffusion will take place. Perfect? Right? Now, my dear students, there comes a term, rate of effusion. How do we define the term rate of effusion? Let's get to know about this as well. Rate of effusion. Let me first of all tell you, there are many ways by means of which you can define the term rate of effusion. Many ways are there by means of which we can define the term rate of effusion. Let's try to understand what those terms exactly are. Let me imagine this is a container. Let's keep some gas molecules inside this container. Right? Let's imagine that suddenly a small hole got created over here. Right? Due to which the gas is coming out. Perfect. Now, my dear students, how do we define the rate of effusion? The first way to define the rate of effusion is volume of the gas. Volume of the gas escaped. Volume of the gas escaped divided by time taken. This is the first way by means of which you can define the rate of effusion. The volume of the gas coming out divided by time taken. For example, imagine that 5 milliliters of gas are coming out in 2 seconds. Imagine that 5 milliliters of gas are coming out in 2 seconds. I want you to calculate the rate of effusion. How much it's going to be? It's going to be volume of the gas escaped. That's 5 ml. Time taken 2 seconds. So it's going to be 2.5 milliliters per second. It means 2.5 milliliters of gas are coming out in just 1 second. Correct? So this is the first way by means of which you can define the rate of effusion. Volume of gas escaped divided by time taken. There is one more way by means of which you can define it. What is that? Number of moles. Number of moles of gas escaped. Number of moles of gas escaped divided by time taken. Divided by time taken. Now imagine that 5 moles of gas. Imagine that 5 moles of gas are coming out of the container in 2 seconds. Imagine that 5 moles of gas are coming out of the container in 2 seconds. And I want you guys to define the rate of effusion. How exactly you're going to do it? Number of moles of gas escaped, that's 5 divided by 2. So it's going to be 2.5 moles per second. 2.5 moles per second. First term, rate of effusion. We defined it in terms of volume. Second way, we defined the same thing in terms of moles as well. Either you want to say volume of the gas escaped divided by time taken, or you can say it in a different way, number of moles of the gas escaped divided by time taken. As simple as that, right? Now it's going to be completely your choice to select the units. If you are using the first formula, in the numerator you'll write the units of volume. In the denominator you'll write the units of time, right? Similarly, as per the second formula is concerned, if you are using the second formula, in the numerator you'll write moles. In the denominator you have to write time. So it's moles per time basically, right? Time can be in seconds, hours, minutes, whatever. Well, there is one more way to define the rate of effusion. How exactly? Distance traveled by the gas molecules. Distance traveled by the gas molecules divided by what? Divided by time taken. This is one more way of defining the rate of effusion. Distance traveled by the gas molecules divided by time taken. Distance you can take in meters, centimeters, or whatever. Time you can take in seconds, minutes, hours, or whatever. This is one more way of defining what? This is one more way of defining the rate of effusion. Perfect. Now, my dear students, one more thing. One more thing. Imagine that the gas is coming out of the container. If the gas is coming out of the container, can I say number of moles of gas inside the container will start to decrease? It's simple. If the gas is coming out of the container, right, the number of moles of the gas inside the container will start to decrease, correct? Because the gas is coming out. Perfect. Or in other words, I can say the number of molecules of gas inside the container decreases with time. And if the number of molecules of the gas inside the container decreases, can I say distance between the molecules inside the container that increases? And if distance between the molecules inside the container increases, what will happen to the number of collisions? Number of collisions inside the container that will decrease. And if number of collisions decrease, the pressure inside the container will start to decrease, right? So what is happening due to this effusion? When the gas is coming out of the container, the pressure of the gas inside the container, that starts to decrease. That starts to decrease. So my dear students, due to effusion, the pressure inside the container, that decreases. So you can define rate of effusion in one more way as well. It's going to be pressure drop, decrease in the pressure of the gas inside, divided by time taken. Divided by time taken. Or you can write it like this. Pressure drop, decrease in the pressure of the gas. Decrease is something which I represent with minus sign. Pressure drop, change in pressure, delta P, divided by time interval delta T. This is one more way of writing the rate of effusion. Perfect. I hope it's clear to everyone. So from now onwards, the rate of effusion you are going to define in 4 ways. Number 1, volume of the gas escaped divided by time taken. Moles of the gas escaped divided by time taken. Distance traveled by the gas divided by time taken. Right? Decrease in the pressure of the gas divided by. Yeah? Let me know once in the chats quickly if everything is clear till here. Let me know quickly, my dear students, in the chats if every single thing is clear till here. Quickly. Quickly. Quickly, people, everyone. Perfect. All right. Perfectly done, guys. Now, if this is clear to everyone, then let's talk about the important law. But before talking about the important law, let me quickly recap the things. First, we defined the effusion. Then we defined the term diffusion. Then I told you effusion is always followed by diffusion, right? Then we defined the rate of effusion in different ways over here, right? Okay. One thing which I want to discuss with you. Whenever from now onwards you'll be talking about the rate of effusion. Rate of effusion. From the term rate of effusion, what kind of idea you'll be getting? Rate of effusion gives you the idea about the speed with which the gas comes out of the container. Rate of effusion gives you the idea about the speed with which the gas comes out of the container. From now onwards, if I say rate of effusion of the gas is more, what does that mean? That means the speed with which the gas comes out of the container, that is more, right? From now onwards, if I say rate of effusion of the gas is more, that means the speed with which the gas comes out of the container, that is more, correct? In other words, if I say the rate of effusion of the gas is less, that means the speed with which the gas comes out of the container, that is less. Okay? So directly you are going to relate rate of effusion with the speed with which the gas comes out of the container. As simple as that. I hope this part is clear to you. If this basics is clear to you, then let's talk about something very important. That's Graham's law of effusion and diffusion. Graham's law of effusion and diffusion. So what this Graham's law of effusion and diffusion is all about? Let me quickly write its statement. Then I'll make you understand what it means. And finally, we can solve different types of questions which can be asked here. Right? Yeah? Have a look, guys. Graham's law of effusion. What it states. What it states. I'm writing at same pressure and temperature. At same pressure and temperature, rate of effusion, or you can say rate of diffusion also, okay? Rate of effusion of a gas is inversely proportional to the square root of the molar mass of the gas. To the square root of the molar mass of the gas. To the square root of the molar mass of the gas. This is the simplest statement of what? This is the simplest statement of the Graham's law of effusion. At same pressure and temperature, rate of effusion of the gas is inversely proportional to the square root of molar mass of the gas. Have a look. Let's try to understand it. Let's try, or before making you understand, I'll write it in the mathematical formulation, right? It means rate of effusion, which I'm representing with R, rate of effusion is inversely proportional to what? It is inversely proportional to square root of molar mass of the gas at same pressure and temperature. So let's try to understand what it exactly means. See guys, imagine that this is the container which you have, correct? Imagine that this is the container which you have. For example, these are the gas molecules which are present inside the container. I'm assuming that the gas inside the container, it's kept at constant pressure and temperature. The gas inside the container, imagine that it's kept at constant pressure and temperature. Now, my dear students, for example, if you create a hole here, this is the hole which got created. Perfect. Now, through this particular hole, what is going to come? What's going to happen? The gas will start to come out of the container. So, effusion will happen. Effusion will happen. Now, what this Graham's law says? Graham's law says rate of effusion. That means the speed with which the gas comes out of the container. That is inversely proportional to square root of molar mass of the gas. More the molar mass of the gas inside the container, less is going to be the rate of effusion. Less is going to be the speed with which the gas comes out of the container. Right? It's simple. Lesser the molar mass of the gas, more will be the rate of effusion. More will be the speed with which the gas comes out of the container. Right? It's evident. Perfect. So, more the molar mass of the gas, lesser the rate of effusion. Lesser the molar mass of the gas, more the rate of effusion. As simple as that. Okay. Well, there's a derivation for this particular result as well, but that's of no need to you. So I'm just giving you the result directly, and I'll show you how to apply it in the questions. Yeah. Simple. Is it clear to everyone quickly? Is it clear to everyone? So do remember from now onwards, that gas which has got more molar mass, the speed with which it comes out of the container, that will be less. That gas which has got less molar mass, the speed with which it comes out of the container, that will be more. As simple as that. Okay. Now people, let's have a look on few more important things. Have a look. Since the gas which is there in the container, I'm assuming that the gas is ideal. If the gas is ideal, if the gas is ideal, then this particular gas has to follow the ideal gas equation. Absolutely. The gas in the container, I'm considering it to be ideal. So it has to follow the ideal gas equation, PV is equal to nRT, right? Or the density form of ideal gas equation, that is PM is equal to dRT, correct? Now people, I'm keeping the pressure and temperature constant. R is already constant, right? So can I say molar mass is directly proportional to density? Molar mass is directly proportional to density. So my dear students, this particular statement which I wrote, it can be also written in terms of density as well, correct? So you can write it like this. You can write it rate of effusion is inversely proportional to square root of, instead of molar mass of the gas, what you'll be writing? You'll be writing the density of the gas. Instead of the molar mass of the gas, you can write the square root of density of the gas as well. Perfect. Since the gas is kept at constant pressure and temperature, and at constant pressure and temperature, molar mass is directly proportional to what? Density. So in this particular statement, wherever you're finding the molar mass, just replace the molar mass by the term density. So either remember this statement in this format or remember the statement in this format. Choice is all yours. The choice is all yours. Okay. Now people, let's try to understand few important things. I'm writing case 1. I'm writing case 1 over here. For example, this is one of the container. And similarly, this is one more container. I've got 2 containers over here. Right? 2 containers I have. 2 identical containers we have. Now, for example, in this particular container, we have got gas A. In this particular container, we have got gas B. The first thing which I'm assuming both the gases to have same pressure and temperature. Let's assume pressure and temperature of both the gases is same. Whatever is the pressure of A, same is the pressure of B. Whatever is the temperature of A, same is the temperature of B. So both the gases, they are present at same pressure and temperature. Let's assume that molar mass of gas A, that's Ma, molar mass of gas B, that's Mb. Perfect. Now, for example, a hole got created here. Similarly, a hole got created here as well. So what is going to happen? The gas will start to come out. Even this gas will start to come out. Imagine that VA volume. VA is that volume of gas A which is coming out of the container in time TA. Imagine that this VA represents that volume of gas A which is coming out of the container in time TA. Similarly, imagine that VB, it represents that volume of gas B which comes out of the container in time TB. Or let me write one more term, Na. These are the moles of the gas A which are coming out of the container in time TA. Similarly, Nb, these are the moles of gas B which are coming out of the container in time TB. Now, dear students, since both the gases are kept at same pressure and temperature, right? Effusion of gas A is taking place as well as effusion of gas B is taking place. Now, if I want you guys to compare the rates of effusion, I want to see which gas has got more rate of effusion, which gas is coming out with more speed. How you are going to do that? How you are going to do that? Few minutes back, I told you, rate of effusion, it's inversely proportional to what? Square root of molar mass of the gas. This is something which I told you, right? Perfect. Now, dear students, rate of effusion of A will be inversely proportional to square root of molar mass of A. Similarly, rate of effusion of B inversely proportional to square root of molar mass of B. Right? I want to compare the rates of effusions. And how exactly? This is how you are going to write it. Rate of effusion of A divided by rate of effusion of B. Just divide the two things. So rate of effusion of A divided by rate of effusion of B. It comes equal to under root of molar mass of B divided by molar mass of A. Perfect. Number 1. In place of molar masses, since the gases are present at same pressure and temperature, so in place of molar masses, you can use the term densities as well. Density of B divided by density of A. Right? Or my dear students, you can do one more thing. Rate of effusion of A. We have defined rate of effusion in different ways over here. I'll say rate of effusion of A is going to be volume of A coming out of the container divided by time taken by A. Similarly, rate of effusion of B is going to be volume of B coming out of the container in time TB. Same thing you can represent in terms of moles as well. Same thing you can represent in terms of moles as well. Rate of effusion of A, moles of A divided by time taken by A, divided by moles of B divided by time taken by B. Right? So this is one very important result which we will frequently use to solve the questions. Yeah? I hope it's clear to everyone. So this is the first result, my dear students, case 1. Now similarly, let me talk about the case 2 as well. Let me talk about case 2 as well. Now imagine the gases which are present in both the containers. Now imagine their pressure is different. Imagine their pressure is different, for example. Imagine their pressure is different. Okay? Imagine their pressure is different. Just their temperature is same. Just their temperature is same. Imagine their pressure is different but temperature is same. Let me assume that pressure of gas A is PA, pressure of gas B is PB. This is something which I'm assuming. Okay? Pressure of gas A is PA, pressure of gas B is PB, and temperature of both the gases is same. Right? The first case, case 1, it was valid when pressure and temperature of both the gases was same. Perfect? The first case was valid when the pressure and temperature of both the gases is same. But the second case which I'm going to show you, I'm keeping the pressure of both the gases different, but I'm keeping the temperature same. Now guys, it's evident. More the pressure of the gas which will be having more pressure, can I say, its speed of escaping out will be more. Imagine this gas is at 2 atm pressure. Imagine this gas is at 10 atm pressure. Perfect? Right? So it's evident that gas whose pressure will be more, right? Its rate of effusion will be more. Right? I'm assuming this particular gas, it has got low pressure, for example 2 atm. This particular gas, it has got high pressure, 10 atm for example. Right? So these gas molecules will be more random. Right? If these gas molecules are more random, they can come out of the gas quickly as compared to gas A. Perfect. So I can say one more thing. Rate of effusion, it is directly proportional to pressure of the gas. And already we know it's inversely proportional to square root of molar mass. Perfect. Already we know it's inversely proportional to square root of molar mass. Now dear students, rate of effusion of A, can I say it's directly proportional to pressure of A divided by square root of molar mass of A? Similarly, rate of effusion of gas B, it is directly proportional to pressure of B divided by square root of molar mass of B. Now, if I want you guys to compare the rates of effusions of these two gases, if I want you guys to compare the rates of effusions of these two gases now, so it's going to be rate of effusion of A divided by rate of effusion of B will be equal to pressure of A divided by pressure of B is going to be under root of molar mass of B divided by molar mass of A. Now, in place of rate of effusion of A, you write volume of A coming out from the container divided by time taken by A. Volume of B coming out divided by time taken by B. Same thing you can write in terms of moles. Moles of A coming out of the container in time TA. Moles of B coming out of the container in time TB. So this is one more relation which you guys are going to remember from now on. And this particular result which I gave you, it's valid when the temperature of both the gases is kept same, but pressure of the gases is kept different. Is kept different. Perfect. The first result is valid when pressure and temperature of both the gases is same. The second result is valid when temperature is same but pressure is different. I hope it's clear to everyone. Yeah. So let me quickly summarize it. Result number 1. If pressure and temperature of both the gases is same, then how do you compare the rates of effusion of the gases? It's going to be Ra divided by Rb is equal to under root of Mb divided by Ma, which can be written as under root of density of gas B divided by density of gas A, which can be also written as volume of A coming out of the container in time Ta, volume of B coming out of the container in time Tb. It can be written in terms of moles as well. Moles of A coming out of the container in time Ta, moles of B coming out of the container in time Tb. Perfect. So this is the first result which is used to compare the rates of effusions of two gases which are kept at same pressure and temperature. Now, case number 2. If pressure of the gases is different, if pressure of two gases is different, but temperature of the gas is same, how do we compare the rates of effusions at that time? RA divided by RB is equal. It's going to be PA divided by PB under root of MB divided by MA. MB divided by MA. Or you can write it as VA divided by TA. In the denominator, you are going to write it as VB upon TB. Similarly, in terms of moles, you can write it as NA divided by TA divided by NB divided by TB. This is one more result which is used in the questions to compare the rates of effusions of those gases which have got same temperature but different pressure. Okay. Now, my dear students, there is one generalized form. There is a generalized form for the rate of effusion. Generalized form for rate of effusion. Do remember this particular thing as well. Rate of effusion, it's directly proportional to pressure of the gas. It's directly proportional to area of cross-section of the hole, area of cross-section of the orifice through which the gas is coming out of the container, divided by under root of temperature of the gas, molar mass of the gas. This is the generalized form. This is the generalized form from which you can keep any two terms constant and accordingly you'll use the result. This is the generalized form. Rate of effusion is directly proportional to pressure of the gas, area of cross-section of the orifice, area of cross-section of the hole from which the gas is coming out. T stands for the temperature of the gas. M stands for the molar mass of the gas. Okay. Now you must be thinking, rate of effusion and temperature. It looks like that they are inversely proportional to each other, right? It looks like that they're inversely proportional to each other. So you must be thinking on increasing the temperature, rate of effusion decreases. On increasing the temperature of the gas, you must be thinking on increasing the temperature of the gas, rate of effusion decreases, right? That's something which you must be thinking. But the case is reverse here. On increasing the temperature, rate of effusion, it increases. On increasing the temperature, rate of effusion increases. Now, how we are going to understand it? Since they look inversely proportional to each other. But I'm telling you, if you increase the temperature, rate of effusion, that increases. Why it happens? Right? Why it happens? Can you let me know why it happens? Anyone? Anyone, dear students? Anyone? So first of all, imagine it like this. Let's say you have got a container in which you have got the ideal gas. Perfect. And this is the hole through which the gas has to come out of the container. Perfect. Now, since this is the ideal gas, so it has to follow the ideal gas equation. PV is equal to nRT. It has to follow the ideal gas equation. Now, imagine that the volume of the gas is constant, right? Imagine that volume of the gas is constant, moles are constant, R is constant. Imagine that. So can I say pressure of the gas will be directly proportional to temperature of the gas? I can say that. I can say that, right? So the ideal gas which is there in the container, imagine that the volume and the moles present in the container, they are constant, for example. R is also constant. So pressure is directly proportional to temperature. Pressure is directly proportional to temperature, right? So that means if you increase the temperature, pressure will accordingly increase. Or I can say, if you double the temperature, pressure will double. If you make temperature 2 times, pressure of the gas will also become 2 times. If you decrease the temperature of the gas by half, pressure of the gas will decrease by half, right? Perfect. I hope this is clear. I hope this part is clear, right? Imagine that the volume and moles are constant, they are fixed, right? Imagine that the gas is not coming out right now. The volume and moles, they are fixed, they are constant. If the volume and moles are constant, I'll say pressure is directly proportional to temperature. So if you increase the temperature, pressure will increase. If you double the temperature, pressure will double. If you half the temperature, pressure will half, correct? Now imagine that you are doubling the temperature. Imagine that you are doubling the temperature, okay? Earlier, let's assume the temperature of the gas was T, molar mass of the gas was M, pressure of the gas was P, area of cross section of orifice was A. Okay, these are the parameters which I'm defining. Perfect. Now, dear students, understand like this. If I use this particular result, I'll say rate of effusion for the gas right now. It's directly proportional to pressure of gas, area of cross section of the orifice, under root of temperature, and this is molar mass. Correct? Let's call this as equation number 1. Perfect. Now, if I double the temperature, right? If I double the temperature, pressure will double. Perfect. Then, what will be the new rate of effusion at that time? That will be directly proportional. Since you are doubling the temperature, so pressure will double. So instead of P, you are going to write 2P. And this is A. Under root of. Instead of T, you are going to write 2T. And this is M over here. Correct? So I can say R dash, that's directly proportional. 2 times, this is P, this is A. Under root of 2 is 1.4, right? And it's going to be under root of T. And this is M over here. Perfect. So R dash is directly proportional to 2 divided by 1.4, and this whole term, this particular term, this is something which you call as R. This is something which you call as R. So R dash is equal to 2 divided by 4. 2 divided by 4 is greater than 1. 2 divided by 4 is greater than 1. Perfect. 2 divided by 4 is greater than 1. It's 1 point something. So R dash comes out to be equal to 1 point something multiplied by R. 1 point something multiplied by R. What does that mean? That means R dash is greater than R. That means R dash is greater than R. So what can you conclude from here? What can you conclude from here? R dash, the new rate of effusion, is greater than that of old rate of effusion. So when we increase the temperature, what happened to the rate of effusion? Since you increase the temperature, what happened to the rate of effusion? Rate of effusion also increased, right? That's something which I wrote over here. This is how you are going to remember it. On increasing the temperature, rate of effusion, that increases. Perfect. On increasing the temperature, rate of effusion, that increases. Right? If you increase the temperature, rate of effusion increase, that does not decrease. So this is something which you guys are going to remember again from now onwards. Is this super clear to everyone? Quickly. Quickly, guys, everyone. Is it clear to everyone quickly? Okay, if this is clear, let's try to solve some questions which will make all these concepts absolutely clear. I'll start with the simplest question. My dear students, a sample of SO2 gas escapes through a hole in 122 seconds. Okay? How long will it take for O2 to effuse the same volume under similar conditions? What does it mean? What does it mean? Have a look. As far as the question is concerned, we have got, for example, two containers. Right? One of the container contains SO2 gas, and one more container, it contains O2 gas. Perfect. The gases are kept under similar conditions. That means pressure and temperature of both the gases same. The gases are kept under similar conditions. That means pressure and temperature of both these gases is kept same. Right? Now understand. Imagine a hole got created here and some volume of SO2 is coming out. Let's say a hole got created, O2 gas is also coming out of the container. For example, it's mentioned that a sample of SO2 gas escapes through the hole in 122 seconds. Let's assume that VML of SO2 gas is coming out of the container in how much time? Is coming out of the container in 122 seconds. Let's assume that VML of SO2 is coming out of the container in 122 seconds. How long will it take for O2 gas to effuse the same volume? We need to calculate how long will it take for O2 gas to effuse the same volume. Let's say VML of O2 is also coming out of the container, and I need to calculate how long will it take for O2 gas to effuse the same VML under similar conditions. All the parameters I wrote. The gases are kept under similar conditions. I'm assuming VML of SO2 is coming out of the container in 122 seconds. I need to check how long will it take for O2 gas to effuse the same volume. So which case this is? Is this related to case 1 or case 2? pressure temperature is same. It is related to case 1. So I'll write rate of effusion of SO2 divided by rate of effusion of O2. It has to be equal under root of molar mass of O2, and this is going to be molar mass of SO2. Correct? Now, rate of effusion of SO2, you can write it as volume of SO2 coming out of the container, time taken by SO2, whole divided by rate of effusion of O2, volume of O2 coming out of the container, time taken by O2. Perfect. Now, dear students, if I relate these two terms, I'm going to relate these two terms. Under root of molar mass of O2 is 32, molar mass of SO2 is 64 grams per mole, volume of SO2 which comes out of the container, that's VML, divided by time taken by SO2, 122 seconds. Volume of O2 coming out of the container, again VML, time taken by O2, I need to calculate. So V and V, first of all, got cancelled. So it's under root of 1 by 2 is equal. It becomes TO2 divided by 122. TO2 divided by 122. Perfect. So you just need to solve it a bit. What you'll be getting TO2 is equal to 122 divided by under root of 2 seconds. Perfect. Or you can write it like this as well. TO2 is equal to 61 under root of 2 seconds. This is how you can write it. So what did we calculate? This is the time taken by O2 gas to effuse the same VML volume as was effused by SO2. That's something which I was supposed to calculate. Say yes or no in the chats if it is clear. So 61 root 2 seconds is the final answer of the question. This is the time taken by O2 to effuse the same VML which I was supposed to calculate. So this was the first question which I'm damn sure you got to know. Let's have a look on one more simple question. Basic question. Basic question. 50 ml of each gas A and B takes 150 seconds and 200 seconds respectively to effuse through the hole under similar conditions. If molar mass of B is 36, what would be the molar mass of A? Here the options are given. Here the options are given. My dear students, you can use the result, you can use the formula, the first formula which we have to solve the question. But I want you guys to solve the question without using the formula. I want you guys to solve this question without using the formula. So basically, you have got two gases. One is gas A and another one is gas B. These are the two gases. As per the question, 50 ml of gas A is coming out of the container. Similarly, 50 ml of gas B is also coming out of the container. It's mentioned, right? Same volume of both the gases coming out. 50 ml of gas A takes 150 seconds to come out. 50 ml of gas B, it takes 200 seconds to come out. Right? So can you let me know which gas is coming out quickly from the container? This gas is only taking 150 seconds to come out. And this 50 ml is taking 200 seconds to come out. So this one is taking more time. This one is taking lesser time to come out. So which gas is coming out from the container with more speed? I'll say A. So can I say rate of effusion of A is greater than rate of effusion of B in this case? Correct? Rate of effusion of A is greater than rate of effusion of B. Now, dear students, one more thing. Molar mass of A we have to calculate. Molar mass of B is given to us, 36 grams per mole. Since you know, rate of effusion is inversely proportional to square root of molar mass. You know that. Rate of effusion, that's inversely proportional to square root of molar mass. Correct? So if rate of effusion of A is more than rate of effusion of B, what does that mean? That means molar mass of A should be less than that of molar mass of B. What is the molar mass of B? That is 36. So molar mass of A should be less than 36. It has to be less than 36, right? And less than 36, there is only one option. That's option A. So that has to be the correct answer. Is it clear? Is it clear to everyone? Quickly, let me know in the chats if it is super clear to everyone, guys. Yeah? Or you can use the direct result. RA divided by RB is equal to under root of MB divided by MA. You just need to put the values and get the answer. This is by looking at the option, you could solve it. No calculations, nothing. Or if you are fine with using the formulas and results, you can do that as well. No issues. The choice is all yours. Yeah? Is it clear? Okay, if it is clear to everyone, let's have a look on one more question then. Let's have a look on one more question. Simple question. See, X ml of H2 gas effuses through a hole in 5 seconds at 5 atm. time taken by O2 gas to effuse the same volume at 10 atm will be. See what the question says. My dear students, again you have got two containers, for example. These are the two containers which we have. These are the two containers which we have, correct? First container is containing H2 gas, and the second container, it contains O2 gas, correct? Now, as far as the question is concerned, X ml of H2 gas, X ml of H2 gas effuses through a hole in 5 seconds. So volume of H2 which comes out of the container, that's X ml, right? And how much time it takes to effuse? Time taken by H2 gas to effuse X ml, that's given to me as 5 seconds. 5 seconds. And this H2 gas, its pressure is also given to me. Pressure of the H2 gas right here is kept as 5 atm. It is 5 atm. Now people, what we need to calculate, the time taken by O2 gas. The time taken by O2 gas to effuse the same volume. So volume of O2 which is coming out is, for example, again X ml, correct? Time taken by O2 gas to effuse the same volume. To effuse the same volume. Time taken by O2 gas to effuse the same XML. At what pressure? At 10 atm. At 10 atm will be. I hope you got the question. Again, I'm repeating the same thing. We have got two gas, H2 and O2. Correct? X ml of H2 gas is coming out of the container in 5 seconds. We need to check how long will it take for the same X ml of O2 to come out of the container. Now look at the question. Is the pressure of the gas the same or different? The pressure is different. The pressure is different. If the pressure is different, which formula are we going to use? Case 1 or case 2? It's going to be case 2 result. So I'll write rate of effusion of H2 divided by rate of effusion of O2. It's going to be equal to pressure of H2 divided by pressure of O2, and this is going to be under root of molar mass of O2, and this is going to be molar mass of H2. Agreed? Yes. And my dear students, rate of effusion of H2, you can write it as volume of H2 coming out of the container, time taken by H2, whole divided by rate of effusion of O2, volume of O2 coming out of the container, time taken by O2. Perfect. Just compare these two things. Pressure of H2 is 5 atm, pressure of O2 is 10 atm, under root of molar mass of O2, 32 grams per mole, molar mass of H2, 2 grams per mole, volume of H2 XML, volume of O2 XML, which are coming out of the container. So it's going to be TO2 divided by TH2. TH2 is 5 seconds. TH2 is 5 seconds. Now a bit of calculation is needed. That's all. So 5 1, this is 5 2. 2 1 2 16. Root of 16 is 4. 4 by 2 is 2. 2 into 5 is 10. So TO2 will come out to be 10 seconds. So what is meant by this 10 seconds? What is meant by the term 10 seconds? What is this 10 seconds here? So this much time is taken by O2 to effuse XML as was done by H2 gas. Perfect. I hope it is again clear to everyone. Perfect, guys. Simple and basic again. All right. If this question is clear to you, let's try to solve one more question. Have a look at this question. Again, a simpler one only. 1 mole of N2 gas at 0.8 atm takes 38 seconds to effuse through a pinhole, while 1 mole of an unknown xenon fluoride at 1.6 atm takes 57 seconds to diffuse through the same hole. The formula of an unknown xenon fluoride will be. See, again, it's a very simple question basically. Have a look how I'm going to solve this. My dear students, as per the question, imagine that we have got two containers. Again, imagine that we have got two containers. Container number 1 and container number 2. In the first container, we have kept N2 gas. In the second container, we have kept an unknown xenon fluoride. Unknown xenon fluoride. We have no idea whether it's XCF2, XCF4, XCF6. We have no idea about that. So it is the unknown xenon fluoride. So let's assume its formula is XEFX. This is the unknown xenon fluoride. It can be XCF2, it can be XCF4, it can be XCF6, right? Now, as per the question is concerned, 1 mole of N2 gas at 0.8 atm. So pressure of N2 gas is given to me as 0.8 atm. Pressure of this XCFX, it will be also given to me as 1.6 atm, right? Now, as far as the question is concerned, how many moles of N2 gas are coming out of the container? number of moles of N2 gas which are coming out of the container is 1. 1 mole of N2 gas is coming out of the container in how much time? In 38 seconds. In 38 seconds. And 1 mole of unknown xenon fluoride is also coming out of the container in how much time? In 57 seconds. This is something which is given. Correct? This is something which is given. 1 mole of N2 is coming out of the container in 38 seconds. 1 mole of unknown xenon fluoride is coming out of the container in 57 seconds. What do we need to calculate? We need to calculate the exact formula of the unknown xenon fluoride. So basically, I need to get the value of this x. Correct? I need to get the value of x. So how I'm going to solve it? First of all, I'll try to compare the rates of effusions of these two gases. I'll try to compare the rates of effusions of these two gases, by means of which I'll calculate the molar mass of XCFX. Once I get the molar mass, I'm done. Have a look how. First of all, the pressure of two gases is different. So let me compare the rates of effusions. So it's rate of effusion of N2 divided by rate of effusion of XCFX. It is going to be equal to pressure of N2 divided by pressure of XCFX. This is going to be under root of molar mass of XCFX divided by molar mass of N2. Agreed? Is equal to rate of effusion of N2. Rate of effusion of N2 I can also write as number of moles of N2 coming out of the container, time taken by N2, whole divided by number of moles of XCFX coming out of the container divided by time taken by XCFX. Correct? I can do this. Now, my dear students, just relate these two. Pressure of N2 is 0.8 atm. Pressure of XCFX, that's 1.6 atm, under root of molar mass of XCFX, I need to calculate. Molar mass of N2 is 28 grams per mole. This term gets cancelled, right? Because 1 mole of each gas is coming out. This is T XCFX, which is 57, divided by T N2, that's 38. Let's try to solve it now. This is 1, this is 2. This is 19.2, this is 19.3. So this 2 and this 2 got cancelled. Square on both the sides, this will become 9. So 9 into 28, 9 into 28 will come out to be 252 grams per mole. So this is basically the molar mass of XCFX, which is what you got. You got the molar mass of XCFX, right? But was I supposed to calculate molar mass of XCFX? No. I am supposed to calculate the molecular formula of XCFX. My dear students, since you got the molar mass of XCFX, can you let me know what will be the molecular mass? Molecular mass. What about the molecular mass of XCFX? Molecular mass of XCFX will be 252. Instead of grams per mole, you'll write U, right? How do you convert molar mass into molecular mass? Just replace the units. In place of grams per mole, you have to write U or AMU. Now, since we got to know the molecular mass of XCFX is 252U, correct? What is molecular mass all about? Molecular mass means sum of atomic masses. Sum of atomic masses of all these elements will be equal to 252, right? So, atomic mass of xenon, it's 131 AMU plus atomic mass of fluorine is 19 AMU multiplied by X. This value comes out to be 252. So, from this value, X value will approximately come out to be 6. So, if you got the value of X, so the molecular formula of this unknown xenon fluoride, which was there in the container, it's going to be XCF6, which I was supposed to calculate as far as the question is concerned. So quickly in the chats, if it is super clear to everyone. Everyone, people in the chats, quickly. Is it clear? Quickly, everyone. Perfect. Let's have a look on one more question. One final question I'm going to show. Let's say the question is like this. Now understand this question. For example, I've got a cylinder like this. I've got a cylinder. Area of cross-section of the cylinder is, for example, A. A is the area of cross-section of the cylinder. Understand this question. Area of cross section of the cylinder is A. Okay. Now, my dear students, let's assume that the length of this particular cylinder, let's say it's 1 meter, for example, or 1 centimeter. Let's say the length of the cylinder is 1 centimeter, for example. Okay. Now, what exactly I'm going to do? Since the cylinder has two ends, from two ends, I'm going to start inserting two gases. From these two ends, I'll start inserting two gases. For example, from this side, NH3 is introduced, and from this side, HCl gas is introduced. On one side, NH3 gas is introduced. On one more side, HCl gas is introduced. Okay? Understand. Simultaneously, from two ends, I'll start introducing two gases. One is NH3, one is HCl. So can I say, when these two gases are introduced, they are eventually going to meet somewhere inside the container? Yes, they are going to meet. And you must be knowing, when NH3 gas reacts with HCl gas, it leads to the formation of NH4Cl solid, which is basically a precipitate. Right? Now you tell me, simultaneously from two ends, I've started introducing two gases. One is NH3, one is HCl. Now they have started coming closer, and there will be a point of contact in the cylinder. And at the point of contact, they'll react, they'll lead to the formation of NH4Cl, and that NH4Cl will get settled down at the bottom in the form of precipitate. Right? That NH4Cl will settle down at the bottom in the form of precipitate. Now, people, can you let me know the precipitate which is getting formed inside the container? Will that precipitate be formed closer towards HCl end or closer towards NH3 end? First, tell me that. Will the precipitate formation takes place closer towards the HCl end or closer towards the NH3 end? What do you think? What do you think? It's simple. See, NH3, its molar mass is 17 grams. HCl, its molar mass is 36.5. Rate of effusion is inversely proportional to square root of molar mass. Lesser the molar mass, more the speed with which the gas moves. So, if simultaneously I'm introducing both the gases, will both the gases move with the same speed? No. I'll say the speed with which NH3 moves, that will be more. The speed with which NH3 moves, that will be more. Correct? Both the gases are introduced simultaneously. Now the speed with which NH3 moves, that will be more. So the gases are going to interact with each other closer to HCl end, and when they interact, let's say this is the line of contact of the two gases. And when the gas interact, they lead to the formation of what? Precipitate, and that precipitate is settled right here at the bottom, for example. This is the precipitate. Now, as far as the question is concerned, the question is like this. The question is like this. Tell me the distance from the HCl end till the precipitate. This distance we need to calculate. And I'm assuming this distance which we need to calculate, let's say that's equal to x centimeters. Let's say that's equal to x centimeters. This is the distance which we have to calculate. We can do it. We can do it, guys. Easily we can do it. See, first of all, a rate of effusion we have defined in many ways. In terms of volume, in terms of moles, in terms of distance traveled as well. In terms of distance traveled as well. And at the same time, in terms of pressure drop as well. Okay? So I can say, if this is x, so this has to be how much? This has to be 1 minus x. It has to be 1 minus x centimeters. Correct? So I'll say rate of effusion of NH3 divided by rate of effusion of HCl will be equal. How much? Will be equal under root of molar mass of HCl divided by molar mass of NH3. Perfect. Now rate of effusion of NH3, I can say distance traveled by NH3. Distance traveled by NH3 from here to here is 1 minus x divided by time taken by NH3, whole divided by rate of effusion of HCl, distance traveled by HCl, which is x, divided by time taken by HCl. And this is equal to under root of 36.5 and this is 17. Okay. Now tell me one thing. Tell me one thing. Time taken by NH3 to reach the precipitate point. can I say that will be same as the time taken by HCl to reach the precipitate point? No doubt, I'm introducing both the gases simultaneously. And NH3 has got more speed. HCl has got less speed. But the time taken by NH3 to start from here and to reach here will be same as that of the time taken by HCl to start from here and reaching here. So time taken by both the gases to reach the precipitate point, that will be same, correct? So T of NH3 is basically same as that of T of HCl, right? So eventually these two terms gets cancelled out. So I got an equation 1 minus x divided by x is equal under root of 36.5 divided by 17. Take the square of both the sides, you'll be getting a quadratic, and from there x value you need to solve, and x value will come out to be 0.4 centimeters. 0.4 centimeters. So 0.4 centimeters from HCl end, the precipitate NH4Cl solid will get formed. Let me know once in the chats if it is again super clear to everyone. Quickly. Quickly, people. Everyone in the chats. Everyone in the chats. Quickly, quickly. Everyone say yes or no. Okay, perfect. Now there is one last type of question which can be asked in your NEET examination, right? There are very tough questions asked in JEE. When it comes to JEE, from effusion, diffusion, I mean, you can relate it with the mole concept, right? And then you can make some tough questions out of this. But in NEET, they don't ask the tough questions. They'll ask these simple questions only, which can be done in 2-3 steps only. That's it, okay? So one more question which they can ask. Let me mark his heading as if the initial molar ratio is given. If the initial molar ratio is given. If the initial molar ratio is given. One more type of question which can be asked. Okay, let me give you its concept first, then we'll see a question which can be asked out of this particular concept. It's simple, guys. Have a look. Now imagine again you have got a container. This is the container. Now, for example, this container, it does not contain only one gas. Let's imagine there are two gases present in the container, gas A and gas B. These are two gases present in the container. Okay. Let's say number of moles of gas A in the container is Na, number of moles of gas B inside the container is Nb. Be careful with the terminologies. I'm saying Na represents number of moles of gas inside the container. Nb represents number of moles of B inside the container. Okay? Or just to make it clear, I'm writing Na inside, right? Nb inside. It means those moles of gas A and gas B which are inside the container. Perfect. Now, my dear students, let's say a hole got created, and through this hole, what's going to happen? Through this hole, only gas A is going to leave, only gas B is going to leave, or the mixture of gas is going to leave? I will say a mixture of gas is going to escape. So this mixture is going to contain some moles of A as well as some moles of B. Let's say Na dash and Nb dash. These are the moles of A and B which are coming out of the container. These are the moles of A and B which are coming out of the container in time t seconds, for example, right? Let's say Na dash and Nb dash. These are the moles of A and B which are coming outside the container. So let me mark them like this. Na dash outside, right? Similarly, Nb dash out. One is inside, one is outside. Okay. Now, dear students, imagine one thing. Since there are two gases, A and B in the container, moles of A in the container is Na, moles of B in the container is Nb. Now use the common sense. More the moles of a gas in the container. Imagine more moles of A are there in the container. Imagine more moles of A are there in the container. If there are more moles of A in the container, can I say there will be more molecules of A in the container? If there are more molecules of A in the container, Can I say more molecules of A will leave from the whole, right? Can I say rate of effusion of A will be more? More the moles of the gas inside the container, more will be the rate of fusion of that gas. Are you clear with this? We have got two gas, A and B, right? I'm assuming that I'm assuming NA is greater than NB. More moles of A are there in the container. More the moles of A in the container, more the molecules of A in the container. More the molecules of A in the container, more molecules of A will leave the container, right? Eventually, rate of effusion of A will be more. So can I simply say something like this? Rate of effusion is directly proportional to number of moles of the gas inside the container, right? And already we know it's inversely proportional to square root of molar mass of the gas, correct? So using this particular result, can I compare the rates of effusions of two gases? Can I say, using this particular result, let me write it somewhere here, just a second. Rate of effusion is directly proportional to number of moles of gas inside divided by under root of molar mass of the gas. Now let me compare the rates of effusion of two gases. RA divided by RB is equal to NA inside divided by NB inside under root of molar mass of B divided by molar mass of A. Can you write it like this? Yes. Now there is one more way of comparing the rates of effusions of the gases, which we have already discussed long back in terms of volume, in terms of moles, in terms of distance, in terms of pressure drop. So rate of effusion of A will be equal to number of moles of A coming outside divided by time taken by A, number of moles of B coming outside divided by time taken by B, right? Since Na dash, Nb dash, these are the moles of the gases which are coming out in time t seconds, right? So both are taking time t seconds to come out. So Tt got cancelled. So Ra divided by Rb is coming out to be Na dash divided by Nb dash. Now, my dear students, look at these two equations. This is the first equation. This is the second equation, right? Ra divided by Rb, Ra divided by Rb. LHS is same. So RHS has to be same as well. So I'll be getting one important result. Na dash divided by Nb dash. It has to be equal to Na inside divided by Nb inside under root of, this is molar mass of B and this is going to be molar mass of A. Perfect. From this particular result, if you remember this result, you can easily solve the question which can be asked from it. I would want every one of you to remember this particular result. It is just be careful. Na dash, these are the moles of A coming out of the container. Nb dash, these are the moles of B coming out of the container. Na inside, these are the moles of A inside the container. Nb inside, these are the moles of B inside the container. Yeah? Perfect. Now, let's see what kind of question can be asked from this particular result. Let's have a look. Let me find a question for you, just a second. Let me find one question for you. Yeah, this is the question. This is the question, guys. Mixture of H2 gas and O2 gas are in 2:1 molar ratio. Okay? Allowed to effuse through a hole. What will be the composition of the mixture coming out initially? What will be the composition of the mixture coming out initially? What does it mean? It means you have got a container. And in this particular container, you have got two gases. You have got H2 and with H2, you have got O2, right? And as per the question, H2 and O2, their molar ratio is given. Number of moles of H2 divided by number of moles of O2 in the container. They are in the molar ratio of 2:1. They are in the molar ratio of 2:1. So these two gases in the container, they are in the molar ratio of 2:1. Now, from this side, mixture of gas will be leaving. So we have to calculate the molar composition of the mixture. So basically we have to calculate N dash H2 divided by N dash O2. This is the value we need to calculate. We have to calculate the molar ratio of the mixture which is coming out from the container, right? This is the molar ratio of the mixture which is coming out from the container. And this whole term we need to calculate. Can you do it? You should be in a position to do it. I told you 5 minutes back only. I gave you one result. I'll say N dash H2 divided by N dash H2 divided by N dash O2 is equal to N of H2, N of O2, which are inside, under root of molar mass of O2, molar mass of H2. See how easy the equation becomes. This is something which we need to calculate. N dash H2 divided by N dash O2. This is something we need to calculate. NH2 divided by NO2. NH2 divided by NO2. This is given to me as per the question, which is 2 divided by 1. Under root of. Molar mass of O2 is 32 grams per mole. Molar mass of H2 is 2. So 2, 1, 2, 16. Root of 16 is 4. 4 2s are 8. So the result comes out to be 8:1. That's the answer of the question. 8:1. This is the molar ratio of the mixture which is coming out from the container initially, my dear students. Is this super clear to you? Quickly, let me know in the chats. Let me know in the chats quickly. Quickly, guys, everyone. Okay. Now let's move on to one more topic. So I hope your effusion diffusion is absolutely clear to you. Okay, one more thing. There is one topic in this chapter, that's KTG, kinetic theory of gases, which involves the molecular speeds, etc. Right? This is one topic in states of matter. But this is one chapter in physics. This is one chapter in physics. KTG, it is one topic of states of matter. But this is one chapter of your physics. Right? So I have talked to Shreya sir. This topic, your KTG, which is one complete chapter in physics, he'll be taking care of it. So I am not going to teach this topic over here. Right? In physics, it's more, it's in detailed format basically. So either he has to do it or I'll have to do it. Perfect. So it's better. This part, this particular topic, which is your one complete chapter in your physics, KTG, right? You'll be discussing this there only. Okay. Is that cool? Is that cool? So Shreya sir will be taking care of this particular topic, KTG, which is one complete chapter of your physics. Okay. Say yes or no in the chats. Is it fine? Yeah. Perfect. Okay. So let's move on then to the real gas part. So till now we were talking about the ideal gas, right? And some important things we discussed about ideal gas. So now is the time to talk about the real gas. So first of all, if you ask me what is the difference between an ideal gas and the real gas, there are two major differences. 2 points are there which will differentiate your ideal gas and the real gas. Okay. Now, my dear students, first of all, how do we define the term ideal gas? There are two postulates of your kinetic theory of gas which actually differentiate your ideal gas from the real gas. So ideal gas is, first of all, it is that particular gas in which there will be no force of attraction or repulsion between the gas molecule. Any type of gas, any gas in which there will be no attraction, any gas in which there will be no attraction or repulsion between the molecules, that gas is what we call as ideal gas. So first postulate of your KTG, which defines the ideal gas. Ideal gas, it is that hypothetical gas. It is that hypothetical gas in which the molecules won't be having any sort of force of attraction or repulsion. Okay, what is a real gas? In the real gas molecules, you will find attraction, repulsion between the molecule. In the real gas molecules, you will find attraction, repulsion between the molecule. Basically, in nature, whatever gases are present in nature, all the gases are real gases. They have got force of attraction or repulsion between their molecules, right? So what is ideal gas? It is just the hypothetical concept. It is a hypothetical concept. It does not exist in reality. Ideal gas does not exist in reality. Okay? Ideal gas, it's a hypothetical concept. Any such gas, by chance, which you will find in which there will be no attraction or repulsion between its molecules, you'll be calling that gas as the ideal gas. Okay? Right? Number one. Number two, the volume of the gas molecule, the volume of the ideal gas molecule is negligible as compared to the total volume of the gas. What does that mean? For example, this is the container in which you are keeping an ideal gas, right? Let's say the volume of the container is V. Let's say this V value is 10 liters. This is the volume of container, for example. Ideal gas molecule, I'm representing it with a dot. That means its size is very, very, very less. So if its size is very less, what about its actual volume? Actual volume, which has to be 4 by 3 pi r cube. It will be very less. The actual volume of the gas molecule, that will be very less, right? And ideal gas, since its size of the ideal gas molecule is very, very, very less. So do remember, the actual volume of the gas molecule is negligible as compared to the total volume of the gas, right? Now imagine how small the ideal gas molecule will be. But if you talk about real gas molecule, you are not going to represent by a dot. You'll be representing it with the help of a sphere. Now, this is the actual volume of the sphere. Now, can you neglect this part of volume as compared to the volume of the gas? No, you cannot neglect it. Perfect. So in short, the ideal gas molecule, its size is negligible. Its actual volume is negligible as that of the volume of the gas. Real gas molecule, its size cannot be, its actual volume cannot be neglected as compared to the total volume of the gas. Okay? Second point. This is something which I'll be teaching in detail afterwards, right? Just remember these points for now. The third point, ideal gas molecules. Ideal gas, it follows this particular equation under all conditions of pressure and temperature. PV is equal to nRT. Real gas molecules, it does not follow this equation under all conditions of pressure and temperature. PV is not equal to nRT for real gas under all conditions of pressure and temperature. But for ideal gas, PV is equal to nRT. For real gas, PV is not equal to nRT under all conditions. Okay, these are the three differences which I would want you guys to remember. Okay, which I would want you guys to remember. Perfect. Number one, in ideal gas, there is no attraction, no repulsion. The size of the ideal gas molecule is very less. The actual volume of the ideal gas molecule can be neglected as that of the volume of the gas, total volume of the gas. PV is equal to nRT for ideal gas under all conditions. Okay, three differences which you need to remember. That's all. That's all. Okay. Now, my dear students, now comes a point. Now we are going to start the real gas part in detail. Okay, now be cautious because whatever I'm going to teach you from now, you might not get it from the books directly. Okay, so be careful with whatever I say from now onwards. Now I'm going to define a term that's called as compressibility factor. Compressibility factor. And my dear students, this compressibility factor, I'm going to represent it with Z. First of all, what is the need of this compressibility factor? See, the compressibility factor which we are going to start now, the compressibility factor is going to let you know how much a real gas deviates its behavior from the ideal gas. It's going to let you know how much the real gas gets deviated from the ideal gas behavior. Or just to make you understand, just remember it like this. Let's say I've got two containers which contains two gases. Now you need to identify which gas is real, which gas is ideal, right? I've got two containers. One contains, for example, both the containers contains two gases, correct? There is one gas here, there is one gas here in this container. Now you need to identify which gas is real, which gas is ideal. Compressibility factor is going to let you know exactly which gas is real and which gas is ideal. So, compressibility factor, it's a tool. It's a tool basically, by means of which we get to know how much a real gas gets deviated from the ideal behavior. Or in simpler words, it tells me that whether the gas in the container is real or ideal. Okay. Now, how exactly? Before going into the details of it, let me tell you one basic statement over here. Imagine that these are the two gas molecules, which are right now at infinite distance apart. These two gas molecules are right now at infinite distance apart. Now, you must be knowing, force of attraction between the gas molecules is inversely proportional to distance, right? Imagine that this is positive charge, this is negative charge, right? Imagine these are unlike charges. So force of attraction between them, that will be inversely proportional to distance. So more the distance, lesser the attraction. More the distance, lesser the attraction. Okay. Now I'm assuming these gas molecules which we have, Let's assume they are right now at infinite distance apart. And when the gas molecules will be at infinite distance apart, force of attraction between the gas molecules will be tending towards zero. So there will be no force of attraction between the gas molecules. There will be no force of attraction between the gas molecules right now. Now people, when these molecules will start approaching towards each other, when they will start coming closer, what will happen to the distance between them? Distance between them decreases. And if the distance decreases, the force of attraction increases. So as the molecules keep on coming closer, the distance between them decreases. Force of attraction increases. Force of attraction increases. Force of attraction increases. Force of attraction increases. Yes. And there will be a scenario when the two molecules will be at maximum closest distance. And when the molecules will be at maximum closest distance, the force of attraction between them will be maximum at that time. So initially when the molecules were at infinite distance apart, the force of attraction between them was zero. Now the molecules are coming closer. The distance between them decreases. Force of attraction increases. There will be a time when the molecules will be at maximum closest distance. And when the molecules are at maximum closest distance, force of attraction between them will be maximum. Now people, if you want these molecules to come a little more closer, now repulsive forces will start between the molecules. Repulsive forces will now start between the molecules. Okay? If you want these molecules to come a little more closer, then repulsive forces will start between the molecules. So what is the point of telling you all this story? The point is, when the molecules were far, attractive forces were existing between them. When the molecules are very close, repulsive forces start to exist between them, right? So can I generalize one simple statement? Attractive forces are long-range forces. Can I say attractive forces are long-range forces? And when I talk about the repulsive forces, they are short-range forces. They are short-range forces. I hope this is clear. Yeah? Attractive forces, they are long-range forces. When the molecules will be far, there will be attractive forces existing between them. But molecules have to be very close, then only repulsive force will start between them. Okay? So attractive forces, these are actually long-range forces. Repulsive forces, these are short-range forces. When the molecules are at infinite distance apart, force of attraction is zero. When the molecules will start coming closer, distance decreases, force of attraction decreases. There will be a scenario when the molecules will be at maximum closest distance. Force of attraction at that time will be maximum. Okay? And after that, if you want the molecules to come a little more closer, which force will exert between them? It's going to be a repulsive force which will start between them. Okay? Right? Is it clear? Is it clear, people? If it is clear, then it is the time to discuss something called as compressibility factor. So what is compressibility factor first of all? Compressibility factor, which I'm denoting by Z. Compressibility factor is going to let us know how much the real gas deviates from the ideal behavior. Or in short, it just tells me whether the gas in the container is real or ideal. Okay? Before making you understand the concept of compressibility factor, there are few ways by means of which this number is calculated. Compressibility factor number is calculated. Number one, the first way of calculating it is Z for the gas. Compressibility factor for the gas is equal to PV divided by nRT. Second way, it's equal to PM divided by dRT. Third way, it's equal to V naught divided by VI. Now, what are these terminologies? One by one, we'll get to know. One by one, we'll get to know what these terminologies exactly are all about. One by one, we are going to discuss them. Okay? Now, guys, let's try to understand the first terminology. Z is equal to PV divided by nRT. Okay? For example, I have got a gas. I have got a gas in the container. Let's say I've got a gas in the container. Okay? Let's say this is the container which contains a gas. I'm assuming pressure of this gas is P, volume is V, number of moles T, temperature T. These are the parameters of the gas. If I know the pressure, volume, number of moles and temperature of this gas, Can I calculate the Z value for the gas? Absolutely, I can do that. Z is equal to PV divided by nRT. P I know, V I know, N I know, temperature I know, right? So I can calculate Z value for the gas. So for example, if the Z value for that gas, if the Z value for the gas comes out to be 1, what does it mean? If the value of Z for the gas comes out to be 1, that means PV divided by nRT value is coming out to be 1. PV divided by nRT value for the gas is coming out to be 1. What does it mean? Just cross multiply it. That means PV is coming out to be equal to nRT. And which gas follows this condition follows this equation under all conditions? It's going to be the ideal gas. That means the gas which we have kept in the container, which gas is it? What is its nature? It's ideal. Yeah? Perfect. So do remember the first point from now onwards. Any gas whose compressibility factor Z value comes out to be 1, that gas is supposed to be ideal in nature. That is supposed to be ideal in nature. That means there'll be no attraction repulsion between the molecules. That means the size of the gas molecule is very less. The actual volume of the gas molecule can be neglected as compared to the volume of the container. I hope it's clear. Number 1. Number 2, if the Z value for the gas does not come out to be 1, if the Z value for the same gas, if it is not equal to 1, what does that mean? That means PV divided by nRT value, it's not coming out to be 1. So what does that mean? That means PV is not equal to nRT. If PV is not equal to nRT, what does that mean? That means the gas in the container, which is that ideal or real in nature? It is a real in nature. It is real in nature. It is non-ideal. Yeah? Right? Now guys, there are 2 more things which we are going to discuss in detail in some time. Just write them up, then we'll discuss them in detail. This point which we discussed, I'm going to divide it into 2 parts. If Z is not equal to 1, that means 2 cases arise. Z can be either less than 1 or Z can be greater than 1. Okay? If Z is less than 1, the gas in the container is going to be first of all real gas. It's going to be real gas. And in this particular real gas whose Z value is less than 1, what do we say? We say the real gas shows negative deviation from the ideal behavior. It shows negative deviation. What this means, you'll get the idea in some time. Just note it first. Right? If Z value for the gas comes out to be less than 1, equal to 1 means ideal. Not equal to 1 means real. Not equal to 1 mein pehli criteria is Z less than 1. The gas is real. It shows which deviation? Negative deviation. And over here, the gas is going to be real only, but it shows positive deviation. Let's get to know one by one what is the meaning of all these things in detail. And the meaning of all these things will be given by this particular result. This particular result is going to make the concept of compressibility factor damn clear to you. So let's try to understand this compressibility factor in detail. Right? Compressibility factor Z. I told you it's equal to V0 divided by Vi. What is V0? We call it as the observed volume. Or you can call it as the real volume as well. Observed volume or real volume. Vi is something which you call as ideal volume. You call it as the ideal volume. Now try to understand what I'm going to say. My dear students, imagine that this is container number 1. This is container number 2. Okay. Imagine that these are 2 containers. Okay. One container, it contains, for example, the ideal gas. Let's say I've got 1 mole of ideal gas in this container. Okay. Let's say I've got 1 mole of unknown gas in this container. I have no idea which gas is it, whether it's ideal or real. No idea about that. Just to make you understand. Okay. One container contains 1 mole of ideal gas. This container contains 1 mole of unknown gas. I have no idea whether this gas is real or ideal. Now, compressibility factor is going to let me know whether the gas in this container it's real or ideal. Okay. Now, dear students, one more thing. Let's assume that both the gases are present at STP, standard temperature pressure. Their pressure and temperature is constant. Pressure is 180, temperature is 0 degrees centigrade. This is something which I'm assuming. Both the gases are present at STP. Let me tell you, volume occupied by the ideal gas, I'm representing that with Vi. volume occupied by this unknown gas, I'm representing that with V naught. I hope these two terms are clear. What is V naught? What is Vi? Volume occupied by the unknown gas. Volume occupied by the ideal gas. Now you must be knowing, if we have got 1 mole of ideal gas in the container, 1 mole of ideal gas at STP, it occupies the volume of 22.4 liters. You know it? 1 mole of ideal gas at STP, it occupies the volume of 22.4 liters. Okay. Now, my dear students, I need to check whether this particular gas in the container is real or ideal. So what I'll be doing, I'll be calculating the Z value for the unknown gas. I'll be calculating Z value for this unknown gas. Okay. If the value of Z for the unknown gas comes out to be 1, that means V naught divided by Vi value has come out to be 1. V naught by Vi is 1. That means V naught has to be equal to Vi. V naught has to be equal to Vi. If V naught is equal to Vi, that means 1 mole of unknown gas at STP is also occupying the volume of 22.4 liters. Does that mean the unknown gas at that point of time, is that real or ideal? It is ideal in nature. It is ideal in nature, right? Perfect. Number 1. Number 2, if the Z value for the unknown gas, if it comes out to be not equal to 1, that means V naught divided by Vi value is not equal to 1. That means V naught is not equal to Vi. V naught is not equal to Vi. What does that mean? That means the unknown gas in the container, is it going to be ideal or real? It's going to be non-ideal. Non-ideal means it's going to be a real gas. It's going to be a real gas. Okay. Now, people, there are 2 cases which will arise here. If the value of Z for the unknown gas is less than 1. If the value of Z for the unknown gas is less than 1. So it is not equal to 1, it's less than 1. Right? So that means the gas right now, this unknown gas, it's a real gas now. It's not unknown, it's real. Because I'm assuming its Z value is less than 1. So it is a real gas. It's a real gas. If Z is less than 1, what does that mean? V naught divided by Vi is less than 1. V naught by Vi is less than 1. What does that mean? That means V naught is less than Vi. V naught is less than Vi. My dear students, I'm assuming this unknown gas which we had in this container, if it is Z is less than 1, so that means it has to be a real gas now. It's not an unknown gas now. It's a real gas. It is a real gas. Whose Z value is less than 1. Whose Z value is less than 1. It's a real gas now. Whose Z value is less than 1. So V naught by Vi is less than 1. V naught is less than Vi. V naught is less than Vi. If V naught is less than Vi, what does that mean? That means volume occupied by the real gas is less than the volume occupied by the ideal gas under same conditions. Volume occupied by real gas is less. When is that possible? When is that possible? Volume occupied by real gas is less. When is that possible? That is possible only when the real gas molecules would have come closer. Right? And when the real gas molecules would have come closer, distance between the molecules would have decreased. Force of attraction would have increased. So do remember that real gas, whose Z value is less than 1. Do remember that real gas whose Z value is less than 1. In that real gas, force of attraction dominates. Force of attraction dominates. Force of attraction dominates. Number 1. Number 2. This is the real gas whose Z is less than 1. This is the ideal gas. Force of attraction dominates here. Here we have got no force of attraction or repulsion. Now, my dear students, you tell me one thing. You tell me one thing. If you want to compress both the gases, imagine that this is the piston here. This is the piston. You want to bring this piston down. You want to drag the piston down. Okay? You want to compress both these gases. This is the gas. This is the real gas whose Z value is less than 1. This is the ideal gas. Now, if you want to compress them both, which gas can be compressed more? Can you imagine that? In this particular gas, the molecules have got force of attraction. That means the molecules have got tendency to come closer. Here, no force of attraction. Molecules have no tendency to come closer. Here, molecules have force of attraction because it's a real gas whose Z is less than 1. Right? Okay, now I want to compress both. Which can be compressed more? This particular gas, whose molecules have the tendency to come closer. The molecules would want to come closer, right? And that gas whose molecules would want to come closer, that gas can be compressed more. So do remember that real gas whose Z value is less than 1, that can be compressed more than that of ideal gas. Then what? Then the ideal gas. I hope it's clear, right? I hope it is clear. Now guys, one more thing. Now what is the last point? Last point is if Z is greater than 1. Now you tell me, if Z is greater than 1. If the Z value for this particular real gas is greater than 1, what will happen? What will happen? Let's get to know. Let's get to know. If the Z value for the real gas is greater than 1, that means V0 divided by Vi value will be greater than 1, which tells you that V0 is greater than Vi, which tells you that V0 is greater than Vi. If V0 is greater, that means volume of the real gas is more. Volume of the real gas is more. What does that mean? Okay, you imagine it like this. Volume of the real gas is more than that of volume of ideal gas under the same conditions. When would have got the volume of real gas more? When volume of real gas would have increased? Volume of real gas would have increased only if repulsive forces between the molecules would have dominated, right? Then only the volume of real gas would have become more than that of volume of ideal gas under similar conditions. Okay, so do remember that real gas whose Z value is greater than 1. Do remember repulsive forces. First of all, the gas is real in nature. And in the real gas, which forces dominate? Repulsive forces dominate. Repulsive forces dominate, right? And my dear students, tell me one more thing. This is a real gas whose Z is greater than 1. Repulsive forces dominate in this gas. Now, I want you guys to compress these two gases. Which gas can be compressed more? Or I can say which gas can be compressed less? This particular gas, its molecules have got repulsion in between them. So molecules do not have any tendency to come closer. Molecules do not have any tendency to come closer. So if you want to compress both the gases, which gas you can compress easily or which gas can be less compressed? The real gas whose Z value is greater than 1 will be less compressible because repulsive forces dominate between the molecules. The molecules do not have any tendency to come closer, right? So do remember, gas is less compressible. The real gas is less compressible than the ideal gas. Are all these points clear to you? Quickly in the chats. Quickly, my dear students, all these points are clear? All these points are absolutely clear, yeah? If all these points are clear, let's try to solve one question then. All these points are absolutely clear. Compressibility factor Z is less than 1. That means the gas is real. Attractive forces dominate. Gas is more compressible than ideal gas. Greater than 1. Repulsive forces dominate. Gas is less compressible than that of ideal gas. Okay? Let's try to solve one simple question. What do you think about this one? 1 mole of the gas occupies 30 liter volume. So you have got 1 mole of the gas. It occupies 30 liters volume, right? Temperature of the gas is kept 273 Kelvin. Pressure of the gas is kept 1 atm. Predict the nature of the gas. We have to check whether the gas is real or ideal. Okay? That means we have to get the value of Z basically. If we get the value of Z, we can easily decide whether the gas is real or ideal. Correct? How do we get the Z value? Z is equal to PV divided by nRT. Right? Pressure is given to us as 1 atm. Volume is given to us as 30 liters. Number of moles, 1. R value, 1 by 12. Temperature, 273. Right? This value will come out to be, this will be 12 into 30. That means 360. 360 divided by 273. It is coming out to be greater than 1. So Z value is coming out to be greater than 1. And if the value of Z is greater than 1, right? That means the value of Z is not equal to 1. So the gas has to be real. So first of all, the gas which is there in the container, that is the real one. And in that real gas, which forces are dominating? Z value greater than 1 means repulsive forces must be dominating in that gas. Repulsive forces will be dominating in the gas. Okay, perfect, simple and basic. Yeah, number one. Let's try to solve one more question. Okay, one more thing. Repulsive force dominate. If repulsive force dominates, the gas will be less compressible than that of ideal gas. So you can check on that parameter as well. You can talk about that parameter as well. The gas which is there in the container, it will be less compressible than that of ideal gas because its Z value is coming out to be greater than 1. One more question in the similar type, Have a look. The density of steam. What is steam basically? Steam is nothing, it's H2O gas. This is what you call a steam. So we have got a gas basically, which is kept at temperature 100 degrees centigrade. Pressure of the gas is 10 raised per 5 Pascal, right? Density of the gas is 0.6 kilograms per meter cube. Again, we have to get the Z value for steam. We have to calculate the compressibility factor for the steam. Now, which formula are we going to use? We have got 3 formulas to calculate Z. One of the formula which I gave you a few minutes back, that was PM divided by DRT. This was one of the equations. Z is equal to PM divided by DRT, right? Now, my dear students, what is P over here? Pressure is 10 raised per 5 Pascal, right? M stands for molar mass of the gas. And molar mass of this particular gas, you know, it's 18 grams. Since you have used the pressure value as per SI system, you are using pressure as per SI system. So you have to use molar mass as per SI system as well, right? You have to use molar mass as per SI system. But we know molar mass of water is 18 grams. Grams is not the SI unit of mass, it's kilograms. So multiply with 10 raised per minus 3. Then only you'll be getting the molar mass in kgs, right? Divided by density, already given as per SI system. What is the value of R as per SI system? It's 8.314. Value of R as per SI system, right? Temperature as per SI system is Kelvin, 373. Now, it's just the matter of calculation. Just solve it, get the value of Z. And Z value is going to let you know whether this steam, whether this H2O gas, it's real or ideal in nature. Let me know once in the chats if it is clear. Let me know quickly in the chats if all these things are clear to you. Everyone, guys. Everyone, quickly. Everyone, quickly. Quickly, people, everyone. Yes, Gopika, you can do that. Just follow the sessions with honesty. Furkana will be doing the inorganic as well, right? Just wait for it. Try to follow one portion completely first. Try to finish it off completely. Then we'll go to inorganic as well. Okay? Perfect. Now comes one more point, one more important point. Variation of compressibility factor with pressure. Variation of compressibility factor with pressure. Okay. Before talking about the variation of compressibility factor with pressure, I told you one point few minutes back. What was that? Z value is equal to V0 divided by Vi. Z value is equal to V0 divided by Vi. Few minutes back I told you. Now you tell me one thing. Z value is equal to V0 by Vi. V0 is the volume of this real gas. Vi is the volume of the ideal gas. You just tell me one thing. If by chance the value of Z for the gas, for the real gas, if decreases, if the value of Z decreases for the real gas, if Z value decreases for the gas, that means V0 value has to decrease. V0 value will be decreasing, right? If the Z decreases for the gas, that means V0 value decreases. V0 value decreases means volume of the real gas decreases. Volume of the real gas decreases means molecules are coming closer. If the molecules are coming closer, distance between them decreases. Force of attraction increases. So do remember, lesser the value of Z for the gas, more the force of attraction between its molecule. That real gas whose Z value will be very less, the force of attraction between its molecules will be very high. Okay? And vice versa, if the value of Z for the gas will be more, do remember, force of repulsion will be more. Force of repulsion will be more. This is one statement which I would want all of you to take a note of. If the value of Z for the real gas is less, that means force of attraction between the molecules will be more. If the value of Z increase for the gas, that means repulsive forces increase for the gas. Okay? Why am I telling you this? Because I need it here. Variation of compressibility factor with pressure. My dear students, first of all, this is the container in which I'm going to keep a real gas. I'm going to keep a real gas. Let's assume the real gas is kept at 0 degrees centigrade. I'm keeping the temperature of the real gas 0 degrees centigrade. Now what I'll be doing, I'll be changing the pressure of the real gas. I'll be increasing and decreasing the pressure of the real gas. And I'll see on changing the pressure, what will happen to the value of compressibility factor of the real gas. I'll check what will happen to the Z value, right? I took a real gas which is kept at 0 degrees centigrade, right? Now I'm going to change its pressure. I'll check what will happen on changing the pressure, what will happen to the Z value for the real gas. Let's get to know about that. So what I'm going to do, I'm going to draw one graph, one curve I'm going to make over here. This is one important curve, okay? This is one important curve, my dear students. Just give me a second. Okay, try to understand what I'm going to do now. My dear students, this y-axis, let's say I'm representing Z on the y-axis, right, with its compressibility factor. On the x-axis, I'm representing pressure. I'm plotting pressure along x-axis. I'm plotting compressibility factor along y-axis. Okay. First of all, at this point, if you go up, the value of Z increases, Let's assume at this particular point, the value of Z is 1. So if I ask you, what is the equation of this whole line? Equation of this whole line is Z is equal to 1. If you take any point, Z is equal to 1. Here, Z is equal to 1. Z is equal to 1. So equation of this particular line is Z is equal to 1. Right? So if I ask you whether this line, whether it represents a real or ideal gas, this line represents the ideal gas. Because on this line, at every point, the value of Z is 1. And the value of Z is 1 for the ideal gases. So this particular line represents the ideal gas. Right? My dear students, the region which is above this line, that will be Z greater than 1 region. And the region which lies below this, that will be Z less than 1 region. Z greater than 1 region means repulsive forces dominate in this region. Z less than 1 region means attractive forces dominate in this region. Attractive forces dominate in this region. Now, my dear students, I need to make a graph. I need to make a curve between Z and P for the real gas and how the curve looks like. The curve starts from here. It takes a dip in the beginning, right? And then it goes up like this. This is the graph. This is the curve between, this is the variation of Z versus P for majority of the real gases. I would say all the real gases except hydrogen and helium. Except hydrogen and helium, all the real gases show the same nature. There is Z versus P curve. First, the graph takes a dip and then it goes up, right? Now, we have to understand basically what this dip means, why it goes down, then why it goes up. We have to understand this a bit in detail. Now, let's try to understand why the graph takes a dip in the beginning, then why the graph goes up. Okay, let's try to understand this. First of all, this white line over here, it represents your ideal gas. Okay. Now, my dear students, at this particular point, can I say at this particular point, I'm approaching the pressure of the real gas 0, the real gas which is there in the container. I'm approaching its pressure as 0. And the graph which I have made over here, this graph is made when the gas was at 0 degrees centigrade, right? Now what I'm doing, I'm keeping the pressure of this real gas approximately 0. That means I'm keeping the pressure of the real gas very less. If pressure of the real gas is kept very less, I would say volume of the real gas will approach towards infinity. You know, P is inversely proportional to V, right? At a particular temperature, pressure is inversely proportional to volume. If pressure is 0, that means volume becomes infinite. Now you tell me, since I'm keeping the pressure of this gas very low, so its volume would have increased. Its volume would have got infinite. Volume of the gas has got infinite. That means volume of the container in which the gas is present, that's infinite. And if the volume of the gas, volume of the container is infinite, for example, that means the molecules will be at infinite distance apart. And when the molecules are at infinite distance apart, force of attraction between them will be 0. Right? And if the force of attraction becomes 0 between the molecules, the gas which was real in nature, when I kept its pressure very low, its volume became infinite, molecules got infinite distance apart, the distance between them got infinite, force of attraction became 0, the gas started to behave like ideal one. Perfect? So do remember, when the real gas, when the pressure of the real gas is kept very low, this real gas, it starts to behave like ideal gas. That's why the curve for the real gas, it started from z is equal to 1 line. It started from this point. It started from this point. So first thing, let me call this as point A. Let me call this as point B. Let me call this as point C. At point A, I must say, real gas was kept at very low pressure. And at very low pressure, your real gas, it starts to behave like the gas. Okay, number one. Number two, if I go in this direction, that means if I go along positive x-axis, that means I'm increasing the pressure of the gas. The pressure of the gas here was 0, volume was infinite, right? The pressure of this real gas at this particular point was 0, its volume was infinite. Now I'm increasing the pressure. If I'm increasing the pressure, volume is getting decreased. If I'm decreasing the volume, see, I'm moving along positive x-axis, I'm increasing the pressure, I'm decreasing the volume. That means molecules are coming closer. At this particular point, the molecules were at infinite distance apart. Now, the molecules are coming closer. If the molecules are coming closer, distance between them decreases. Force of attraction increases. And when the force of attraction increases, the value of Z, that will decrease. That's why on increasing pressure, on decreasing volume, force of attraction between the molecules, that increases. Therefore, Z value decreases. I hope it's becoming clear to you. Yeah? Perfect. Let me repeat the same thing again. At this particular point, pressure of the real gas was 0. Right? It was very less. The real gas was behaving like the ideal gas. Volume of the gas at this point was infinite. Okay? Now, I'm moving in positive x-axis direction. That means I'm increasing the pressure of the gas. I'm decreasing the volume of the gas. Initially, the gas, its volume was infinite. Now you are increasing the pressure. You are decreasing the volume. The molecules are coming closer. Distance between them decreases. Force of attraction increases. And if the force of attraction increases, Z value has to decrease. That's why when you move in plus x-axis direction, Z value is decreasing. Force of attraction is increasing. Can I say this is the minimum value of Z? This is the minimum value of Z. Minimum value of Z means at point B, force of attraction between the gas molecules will be maximum. And when force of attraction between the gas molecules will be maximum? When the molecules will be at maximum closest distance. The molecules right now are at maximum closest distance. Okay. Now, dear students, after this point B, if you further want these molecules to come closer, if you want to increase the pressure a little more, that means you want these molecules to come a little more closer. What will happen? Repulsive force will start. That means Z value will increase. Repulsive forces has started. Z is increasing. Repulsive force is increasing. Z is increasing. Repulsive forces are increasing. This is the point, my dear students, at which the magnitude of attractions and magnitude of repulsions becomes equal. So I must say at point C, the net force on the molecule becomes 0. If net force on the molecule becomes 0, that means again, this real gas, it becomes ideal in nature. So at point C also, the real gas becomes ideal in nature. Okay. Now after point C, if you further want to increase the pressure, now repulsive force will dominate in the gas. So I took real gas in the container at very low pressure, where its volume was infinite. The molecules were at infinite distance apart, force of attraction was 0. The real gas was behaving like the ideal gas. Now if you increase the pressure, volume will decrease, molecules will come closer, distance between them decreases, force of attraction increases, right? So Z value is decreasing with time. This is the minimum value of Z. So at this point, the molecules will be at maximum closest distance. Force of attraction between them will be maximum. And after this, when you increase the pressure a little more, when you want the molecules to come a little more closer, repulsive forces will start. They won't dominate, they'll start. That's why the graph is coming up. At this point, attractive forces were maximum. Now the repulsive forces are starting. But still attractive forces are dominating only. Repulsive forces are just starting. They're increasing. At this point, attractions and repulsions, they become equal. And if attraction and repulsion becomes equal, net force on the molecule becomes 0. If net force on the molecule becomes 0, that means again at point C, the real gas, it behaves like the gas. And after this point, repulsive force dominates between the gas. Right? Is this clear? So my dear students, there are a few things which you need to know. As the value of Z decreases, attractive forces increases. You know it. As the value of Z increases, attractive force decreases, repulsive force increases, which I told you already, right? One more thing. The distance from here till here, this is called as dip of the curve. Okay? This is called as the dip of the curve. So do remember, more the dip of the curve, lesser will be the value of Z. Lesser Z means more attractive force. Okay, so do remember this particular point as well. More the dip in the curve, more is the force of attraction between the gas molecules. Okay. And more the attraction between the gas molecules, what does that mean? That means the molecules have got high tendency to come closer. It means the gas will be more compressible. If the gas is more compressible, the gas can be easily liquefied as well, right? The gas can be easily liquefied as well. Okay? The gas can be easily liquefied as well. For example, I'm giving you one small question like this, just to make you understand things. Let's say this is Z here, this is pressure. Perfect. This line, it represents Z is equal to 1. Now I'm giving you some curves like this. This is valid for gas A, this is valid for gas B, this is valid for gas C. Can you first of all tell me which gas has got least value of Z? Which gas has got least value of Z? C value has got least, then followed by B, followed by A. Lesser the value of Z, more the force of attraction. So gas C has got more force of attraction than B, then A, right? More the force of attraction, more the tendency for the molecules to come closer. And more the tendency of the gas molecules to come closer means easily the gas can be converted into a liquid. See, when the gas molecules start coming closer, what does that mean? The gas starts to get converted into a liquid basically. When the gas molecules come closer, that means the gas starts to get converted into a liquid, right? So those gas molecules in which the molecules have got more tendency to come closer, that means that gas has more tendency to get liquefied. So if I ask you which gas can be liquefied more or less, ease of liquefaction, which gas can be liquefied easily? The molecules whose force of attraction are maximum, right? That gas in which the molecules have got maximum force of attraction, that can be easily liquefied. Okay, perfect. So I would want few points to write over here. So first point, at point A, when the pressure of the real gas was approximately 0, the real gas behaves like the ideal. The gas behaves like ideal. Number 2, at point B. What happens at point B? At point B, Z value is minimum. Therefore, force of attraction between the molecules is maximum. Force of attraction between the molecules is maximum. Right? And I can say the molecules are at maximum closest distance. The molecules are at maximum closest distance, right? Now, one more point. At point C, what happens at point C? Force of attraction and repulsion becomes equal. Therefore, net force on the molecule becomes 0. If net force on the molecule becomes 0, what does that mean? That means the real gas again behaves like the ideal one, right? And after point C, it's a repulsive forces which dominate between the gas molecules. Repulsive forces dominate between the gas molecules, right? Okay, one question if I ask you, in the region A to C, which forces dominate? A to C region, it lies in Z less than 1 region. A region A to C, do remember, it means force of attraction dominates, right? Don't think in A to B it dominates, in B to C it does not. No, right? It's A to C which comes below the Z. Z is equal to 1 line, therefore, right? Therefore, force of attraction dominates in the region A to C. And after C, you can say force of repulsion dominates between the gas molecules. No doubt, force of attraction starts to increase from A to B. And at point B, force of attraction is maximum. After that, repulsion starts. It does not dominate, but force of attraction is maximum here. And after that, force of repulsion starts. It does not dominate. It starts. And here, attraction repulsion becomes equal. Then repulsion dominates. Okay? Be careful with all these things as well. I hope all these things are super clear to you. Right? So, now is the time to talk about the van der Waals gas equation and see exactly what kind of questions can be asked from this particular topic. So quickly, tell me one thing in the chats, whether every single thing is clear till here or not. Quickly, guys. Yeah? You must have studied van der Waals equation, right? So let's get to know how exactly van der Waals equation came and what is its meaning. See, guys. First of all, as far as the ideal gas equation is concerned, what is the ideal gas equation all about? You know it. It is pressure of ideal gas, volume of ideal gas is equal to nRT. This is something which you call as ideal gas equation. This is something which you call as ideal gas equation, correct? Now, ideal gas equation is followed by ideal gases under all conditions of pressure and temperature. Now, real gases, which equation real gases follow? Which equation real gases follow under all conditions? My dear students, real gases, they follow van der Waals equation under all conditions of pressure and temperature. They follow van der Waals equation. Okay. Now, what this van der Waals equation is all about? How do we get it? Dear students, I'm going to make some corrections in this particular equation. I'm going to make some corrections into this particular equation, right? And then I will be getting the van der Waals equation. What kind of correction I'm talking about? Say, instead of Pi, I'm going to write P plus delta P. Instead of Vi, I'm writing V minus delta V is equal to nRT. This particular equation which I wrote over here, this is basically your van der Waals gas equation. And these terminologies which I mentioned over here, this delta P and delta V, this delta P is something which we call as pressure correction factor. This is something which you call as pressure correction factor. And my dear students, this delta V is something which you call as volume correction factor. Now you must be thinking, why did I add delta P over here? Why did I subtract delta V over here? And what this delta P, delta V exactly means? So that's something which we have to discuss in detail, right? So let's try to discuss this pressure correction factor, the volume correction factor in detail so that we can understand how the van der Waals gas equation came, okay? So the first point which we shall be discussing, that is going to be the pressure correction factor. Let's get to know why did we add the term delta P and why did we subtract the term delta V, right? See what we did exactly. Instead of Pi, I wrote P plus delta P. So I added one term delta P over here. I subtracted one term delta V over here. And then I wrote as equal to RT. The point is, why did we do that, right? Have a look. Understand. Now imagine that again you have got two identical containers. Let's say you have got two containers. These are the two containers, okay? My dear students, let's assume that one container contains ideal gas and one more container, it contains real gas. Let's assume these things. One container contains ideal, one container contains real gas. These are the ideal gas molecules, which I'm representing with the help of dots. These are real gas molecules, which I'm representing with the help of spheres, okay? Now, you know, between the ideal gas molecules, you won't find any attraction. But between the real gas molecules, you will find attraction, right? You'll find attraction. Now, imagine that this particular ideal gas molecule is going to collide with the wall of container. At the same time, this particular molecule, it's also going to collide with the wall of the container, right? This molecule is going to collide with the wall of the container. Even this particular molecule, it's going to collide with the wall of the container. Both the gases, we have ideal, we have real. Perfect. We have ideal, we have real. Right? This particular molecule is going to collide. Even this molecule is going to collide. My dear students, this is the ideal gas molecule. Right? When the molecule is going to get collided with the wall of the container, there is no other molecule which is attracting this molecule towards itself. Because it's ideal gas. Molecules do not attract or repel each other. Perfect. So this molecule is going to collide with the wall of the container. But when this particular molecule starts to collide with the wall of the container, the other molecules will be attracting the same molecule towards itself. Because it's a real gas in which attractions exist. When this particular molecule is going to collide, at the same time, the other molecules will be attracting the molecule towards itself. Due to which, if I ask you, which molecule, ideal gas molecule or real gas molecule, which molecule will exert more pressure on the wall of the container? What do you think? What do you think? Ideal gas molecule or real gas molecule? Which molecule will exert more pressure on the wall of the container? Isn't it going to be ideal gas molecule? Right? Because when the real gas molecule goes for the collision, the other molecules attract the molecule towards itself. Yeah? So, pressure of ideal gas will be more than that of pressure of real gas. Absolutely clear? We got to know pressure of ideal gas is greater than that of pressure of real gas. Perfect. Now, my dear students, we got to know pressure of ideal gas is greater than that of pressure of real gas. Okay, is greater than that of pressure of real gas. Since this term is more, this term is less. If I want left hand side and right hand side to be equalized, see, Pi is more than PR. But if I want LHS side to be equal to RHS side, can I say on this side I'll have to add one term, then only left hand side and right hand side will become equal? Right? I can say that. So Pi is equal to PR plus delta P. Right? Pressure of ideal gas is equal to basically pressure of real gas plus I added one term over here such that LHS side and RHS side becomes equal. That's why, if you remember, instead of Pi, I wrote PR plus delta P. Instead of Pi, I wrote PR plus delta P. And this delta P is what we call as pressure correction factor. It's what we call as pressure correction factor. Okay. Now you must be thinking, what this pressure, how do we calculate this pressure correction factor? Let's get to know about that. How do we calculate this pressure correction factor, my dear students? Okay, you must be thinking about that. For example, this is the container which I have. Okay, this is the container which I have. Let's assume in this container, I have got real gas molecules. Everywhere I have got real gas molecules. Everywhere, what do I have? I have got real gas molecules. Everywhere. These are the real gas molecules, for example. Okay, these are the real gas molecules. Now, what do I have to discuss? I have to discuss about pressure correction factor delta P. Delta P. Now, on what factor this pressure correction factor depends upon? Let me tell you. My dear students, what I'm going to do, I'm going to take 2 unit volumes over here. This is 1 unit volume. This is 1 more unit volume. For example, I took 2 unit volumes. This is 1 unit volume. This is 1 more unit volume. In this unit volume, there are gas molecules. Even in this unit volume, you'll find the gas molecule. I'm assuming that the molecules in this particular unit volume, they are going to collide. And I'm assuming that the molecules in this unit volume, they are going to attract the molecules in the other unit volume towards itself. Okay? The molecules in this particular unit volume, they are going to collide. The molecules in the other unit volume, they are going to attract these molecules towards itself. Let me tell you this pressure correction factor. The pressure correction factor, it depends on 2 things. It depends on number of molecules per unit volume, which are going to collide. I'm talking about these molecules. And number of molecules per unit volume, number of molecules per unit volume, which are going to attract the other unit volume molecules towards itself. So can I say your delta P over here, it's directly proportional to, it came out to be n square divided by v square. N square divided by v square, right? My dear students, what is N? N stands for number of molecules, right? Have you ever studied number of moles is equal to number of molecules divided by Avogadro's number? Yes. So number of molecules is equal to number of moles multiplied by Avogadro's number. Perfect. So I can say your delta P, it's directly proportional. Number of molecules means number of moles into Avogadro's number. Number of moles into Avogadro's number. A square divided by v square. Divided by v square, right? Perfect. Now let's have a look on this particular statement. We got to know your delta P. That's directly proportional. Delta P is directly proportional to, we got to know n square, Na square divided by what? N square, Na square divided by v square, right? Divided by v square. Okay. Now since this Na, it is the Avogadro's number, it is a constant basically. So send this constant in the proportionality. If you send the constant in the proportionality, so delta P will be directly proportional to n square divided by v square. Perfect. Now remove the proportionality sign. If you remove the proportionality sign, there will be a constant. Constant is A. So this is n square divided by v square. This is the final result which you have to remember. Your pressure correction factor delta P has to be equal to A n square divided by v square. This particular A over here, it's called as Van der Waals constant. It's called as Van der Waals constant. And this Van der Waals constant A, it gives me the idea about the force of attraction between the gas molecules. It gives me the idea about the force of attraction between the gas molecules. And let me tell you, more the value of A for the gas, more will be the force of attraction between the gas molecules. More the value of A means more the force of attraction between the gas molecules. Now you must be thinking why? More the value of A, more the force of attraction between the gas molecules. So let's have a look why it happens. All right. See guys, I told you Pi is equal to PR plus delta P, correct? So can I say Pi minus PR? Can I say Pi minus PR is equal to delta P? Right? Perfect. So can I say Pi minus PR is equal, delta P is basically AN square divided by V square, right? So more the value of A, more the value of A, more is the difference between these two. More is the difference between, more the value of A means more the difference between these two. When can be difference between these two more? The difference between these two will be more when PR will be less. The difference between these two will be more only when PR will be less. PR less means pressure of real gas has to be less. When will be the pressure of real gas less? When this particular molecule will be colliding with lesser force. When this molecule will collide with lesser force? When the other molecules are attracting this particular molecule with more force, right? That means force of attraction between the molecules will be more. Okay, that's what I wrote, if you remember. More the value of A, more the value of A, more the force of attraction between the gas molecule, right? At the same time, if you ask me, what are the units of A? If you ask me what are the units of A, my dear students, you know your delta P. It's equal to AN square divided by V square. So from here, can we calculate A? A has to be equal to delta P, V square divided by N square, right? So what are the units of A? This is pressure basically. So ATM. Volume square means liter square per mole square. So this is the unit of A, which you guys are going to remember from now onwards. So more the value of A, more the force of attraction between the gas molecules. Correct? More the force of attraction between the gas molecules. I hope this is clear. Can you let me know in the chats once if it is clear? Quickly. So delta P, which I used in the van der Waals equation, that's equal to AN square by V square, right? Quickly in the chats. Okay, what do you think about this one? What do you think about this particular one? Just let me know in the chats. For example, I'm making a graph over here. I'm making a graph over here between Z and P. Okay. This is, for example, Z is equal to 1. This is one gas, gas A. We have got one more gas B. We have got one more gas C. Can you arrange these three gases on the base of A value? Can you arrange these three gases on the base of A value? I told you, more the value of A, more the force of attraction. More the force of attraction, lesser the value of Z, if you remember. So which gas has got least value of Z? C, right? Z order. C is minimum, followed by B, followed by A. Lesser Z means more force of attraction. Force of attraction in C is more than that of B, than that of A. More force of attraction means more the value of A. So A value has to be maximum for C, followed by B, followed by A. Right? I hope you're getting it. Correct? Is this clear, guys? Is this clear to everyone? Quickly. So C value greater than B, greater than A. I mean, A value for gas C is more than that of B, than that of C. Sorry, A value for C is more than that of B, than that of A. Okay. So what did we get till now? We got to know the value of what? We got to know the value of delta P. And this delta P, it came out to be what? It came out to be AN square divided by V square. Now is the time to get the value of delta V. Let's get to know what this delta V exactly is all about. This is again important. So I'm marking the heading over here as volume correction factor. Volume correction factor. Volume correction factor, which is represented by what? It is represented by delta V. Now, my dear students, before talking about the volume correction factor, let's get to know what volume is all about. How do we define the term volume? How do we define it? Volume is defined as the free space available for the gas molecules. The free space available for the gas molecules to move. the free space available for the gas molecules to move defines the volume of the gas. What is meant by that? What is meant by that? Let's have a look. First of all, from now onwards, whenever I'll be talking about the volume of gas, what does that mean? That means I'm talking about the free space available for the gas to move. Now let's try to understand it a bit more in detail. Imagine that this is the container. Imagine that this is the container, right? And in this particular container, I've got two real gas molecules. These are the two real gas molecules. Okay, these are the real gas molecules. Let's assume the volume of the container is capital V. This is the volume of container, capital V. I've got two real gas molecules. Okay, my dear students, for example, if I seize the motion of one particle, if I make sure this particle comes at rest, for example, just to make you understand, I'm making sure that this particle comes at rest. Now, look at the other particle. Look at the other particle. This is the other particle, right? This particle can go everywhere. It can go everywhere in the container. It can go everywhere in the container. But can this particular particle penetrate the volume, the actual volume which this particle has occupied? No. This particular particle, it can go everywhere except the actual volume occupied by this particular particle, right? So if I ask you, what is the free space available for the molecule to move? Is it the whole volume of container? No, it is not the whole volume of container which is the free space available to move. It is the volume of container minus something, excluding some volume, right? So free space available for the gas to move is something which you call as volume of gas. It is equal to volume of the container minus, there is one term which you need to subtract, right? Which you need to subtract. And why this term comes? Because of the actual volume of the real gas molecule, which cannot be neglected. Basically, right? I mean, this particular molecule, it can go everywhere except this particular shaded part, except this shaded volume over here. It can go or else everywhere. Okay, so that's why you can see free space available for the gas to move is something which you call as volume of gas. That will be equal to volume of container minus something which I need to subtract. And this is the something which you need to subtract. It is something which you call as excluded volume. It is something which you call as excluded volume. Okay. Now you must be thinking, you were thinking that why did I subtract this delta V over here? Now you got to know why did I subtract it? Okay, why did I subtract this delta V from the total volume of the container? Okay, one more thing. Imagine that this is one more container in which you have got ideal gas molecule. The actual volume of ideal gas molecule is negligible, you know it. The actual volume of ideal gas molecule is negligible. Imagine that one of the molecule comes at rest. This other molecule, where all it can go? It can go everywhere. Right? The actual volume of this molecule is negligible. That is negligible. So, what is the free space available for this molecule to move? It's entirely the volume of container. So, can I say for the ideal gas? For the ideal gas, delta V has to be 0, right? So I could say volume of the ideal gas is always equal to what? It's always equal to volume of the container. Absolutely. Volume of the ideal gas is always equal to the volume of container in which it is kept. So whatever you have studied till now, we used to say a gas occupies the volume of container in which it is kept, right? What is that? That's not true always. That's only true for the ideal gas, right? For the ideal gas, volume of the gas is equal to the volume of container, not for the real gas. For real gas, volume of the gas is equal to volume of container minus delta V. Some term which you have to extract these. Now this delta V is something which you call as excluded volume, right? The point is, how do we get the value of delta V? Let's see what this excluded volume, what its value exactly is all about. This is again important. See guys, imagine this is very important, okay? Have a look. You might not understand all this in the books. And in the books, it's not given in the detailed format to understand it. This is the container which we have, which is closed on all the sides, okay? Let's assume that I'm taking two real gas molecules here. This is one molecule. This is one more molecule. Two real gas molecules I've taken. Understand it properly now. Okay, two real gas molecules I've taken. Let's assume the radius of the real gas molecule is R. The radius of the real gas molecule is R. Now, dear students, this particular molecule, let's imagine I'm seizing its motion. I'm making sure that this molecule comes at rest, right? This molecule, imagine that it's at rest. The other molecule, it can collide this particular molecule, either is in this direction, or this molecule can come from this side and do the collision, or it can come from this side and do the collision. It can come from this side, do the collision. It can come from this side, do the collision, right? Or this molecule can come from the front side, do the collision, or this molecule can come from the back side and do the collision, right? That are all the possibilities. All the possibilities. Let's imagine that this molecule, let's imagine that this particular molecule is coming from this side and does the collision with the selected molecule. Like this, okay? Same molecule can come from this side as well and will do the collision. Same molecule can come from this side as well and will do the collision. Same molecule can come from this side as well and do the collision. Same molecule can come from the front side and do the collision. Same molecule can come from back side and do the collision, right? Now, dear students, let's assume this is the center of mass of this particular molecule. Center of mass of this one, center of mass of this one, center of mass of this one, center of mass of front one, center of mass of back one. If I join all these center of masses, after joining all these center of masses, will I be getting a circle or it is actually a sphere? What do you think? It looks like a circle, but it's not a circle, it's a sphere. Because the same molecule can come from the front side. It can come from the back side as well. So you have to join all these center of masses. You'll be getting a spherical region over here. You'll be getting a spherical region over here, right? You will be getting a spherical region over here. Yeah. Now, dear students, can this particular molecule, can it come a little more closer? It cannot come a little more closer. That means the center of mass of this molecule, can it penetrate this particular region? It cannot enter into this region. It cannot penetrate into this region. Okay. So see, this particular center of mass, it can go everywhere. It can go everywhere in the container, but it cannot penetrate in this particular region. So this particular region, it becomes the excluded volume for the bimolecular collision. So for bimolecular collision, what is the excluded volume? For bimolecular collision, what is the excluded volume? This whole volume is the excluded volume, right? This spherical region which I got, radius of this spherical region will be R plus R, which makes it 2R, right? R plus R, which makes it 2R. So the excluded volume for two molecules. The excluded volume for two molecules becomes equal to 4 by 3 pi 2R ka cube, which comes out to be 8 multiplied by 4 by 3 pi R cube. Perfect. So excluded volume for two molecules is this much. If excluded volume for two molecules is this much, what about excluded volume for one molecule? What about excluded volume for one molecule? For one molecule. Excluded volume for two molecules is this much. For one molecule, divided by 2. It's 4 multiplied by 4 by 3 pi R cube. Perfect. Excluded volume for one molecule is this much. What about excluded volume for Na molecules? How much it comes out to be? 4 multiplied by 4 by 3 pi r cube multiplied by Na, right? Multiplied by Na. This is the excluded volume for, this is excluded volume for Na molecules if there are Na molecules in the container. Now you have to think. This is the excluded volume for Na molecules. Or I can say this is the excluded volume for 1 mole of gas. Na molecules means 1 mole of gas, right? If this is the excluded volume for 1 mole of gas, tell me, what about the excluded volume for n moles of gas? Excluded volume for n moles of gas will be 4 multiplied by 4 by 3 pi r cube multiplied by Avogadro's number multiplied by n, right? This is the excluded volume for n mole of gas, right? This is the excluded volume for n mole of gas. Now, my dear students, if you look at it carefully, 4 is constant, 4 by 3 constant, pi is constant, r is the radius of molecule constant, Na is a constant, right? So this whole term from here to here, I represent it with B. I represent it with B. So excluded volume for n mole of gas. Excluded volume for n mole of gas. Excluded volume for n mole of gas, I am representing it with delta V. Excluded volume for n mole of gas came out to be n times B. It came out to be n times B. And what is this B all about? B is a constant whose value actually is 4 multiplied by 3, 4 into 4 by 3 pi r cube multiplied by Avogadro's number. Multiplied by Avogadro's number. This is the actual value of B. This is the actual value of B, right? Now, one more thing. This B I can write in one more format. 4 multiplied by. What is 4 by 3 pi r cube? This is the actual volume of one molecule multiplied by Avogadro's number. Actual volume of one molecule multiplied by Avogadro's number. Does that give me the actual volume? Does that give me the actual volume of 1 mole of gas molecules? Does that give me the actual volume of 1 mole of gas molecules? This is again important, right? This B is again the van der Waals constant. It is equal to 4 multiplied by the actual volume of 1 mole of gas molecule. I hope you got it. I hope you got it. Now, dear students, if you ask me what kind of idea this B gives me, see, if the value of B is more, that means the radius of the molecule is more. If the radius of molecule is more, that means molecule is bigger in size. That means molecules are bigger in size, right? So do remember, B gives us the idea about the size of the gas molecule. More the value of B for the gas, more the size of the gas molecule. Perfect. A gives me the idea about force of attraction between the molecules. But this B gives me the idea about the size of the gas molecule. B gives me the idea about the size of the gas molecule. More the value of B, more the size of the gas molecule. Yeah? Is this clear till here? More the value of B, more the size of the gas molecule. Now you must be thinking, what about the units of B? What about the units of B? Since you got to know, your B is equal to delta V divided by N. Delta V is liter, so it's liter per mole. So liter per mole is basically the unit of B over here. Okay? So my dear students, till now, we are done with volume correction factor, we are done with pressure correction factor, right? So the complete van der Waals equation, how does it look like? Now your complete van der Waals equation. Let's see exactly how it looks like. Van der Waals equation. It's going to be P plus delta P, and delta P is nothing, that's AN square by V square, multiplied by V minus delta V, and delta V is equal to N times B is equal to nRT. This is something which you call as van der Waals gas equation. This is something which you call as van der Waals gas equation. And in the van der Waals gas equation, we got two constants, A and B. A gives me the idea about the attraction between the molecules, and B gives me the idea about the size of the molecules. I hope it is again clear to you, right? Is it clear to everyone? Is it clear to everyone, people, quickly? So, this A, it gives me the idea about attractions. That means this term the term in which A is present. This term gives me the basically idea about attraction because this whole term includes A. This term over here, which includes B, it gives me the idea about the size of the molecule. The size of the molecules. I hope it's clear to everyone. Yeah? Kishore, what are you trying to say? Sir, do you conduct NCERT book? What does that mean? Are you asking, do you consult NCERT? In physical, no need to consult NCERT. NCERT is for inorganic and organic, right? Physical, your notes are enough. Perfect? Perfect, guys? Okay, if you got it, then tell me the answer of this question. I'm giving you a question like this. Let's say this is one container. It contains gas 1. We have got one more container. It contains gas 2. It contains gas 2. Let's assume B value for both the gases is same. B value for both the gases is same. A value for gas 1 is more than. A value for gas 1 is more than that of A value for gas 2. This is something which I'm assuming. Now you tell me, which gas has occupied more volume? Which gas has occupied more volume? What do you think? Gas 1 or gas 2? Quickly. Gas 1 or gas 2? Quickly. There are two gases, gas 1 and gas 2, right? B value is same for both the gases. A value for gas 1 is more than that of A value for gas 2. Now you have to tell me which gas has occupied more volume. Quickly. Quickly, everyone. Everyone in the chats. See, B value for both is same. That means both the molecules of gas 1 and molecules of gas 2, they will have same size because B gives me the idea about size. A value for 1 is more. That means attraction between the gas 1 molecules is more, right? If attraction between gas 1 molecules are more, that means molecules would have come closer. Distance would have decreased. If molecules are coming closer, that means the volume of the gas would have decreased. So volume of gas 1 is less than that of volume of gas 2, right? Volume of gas 1 is less than that of volume of gas 2. That means gas 2 has occupied more volume. Gas 2 has occupied more volume. Okay? Perfect. Gas 2 has occupied more volume. Now you tell me, what is the criteria for the gas to get liquefied easily? Tell me that. What is the criteria for the gas to be liquefied easily? Quickly. Quickly, guys. Sudarshan, that comes in kinetic theory of gases, okay? And kinetic theory of gas, Shreyas sir is going to teach you. What is the criteria for the gas to be liquefied easily? First of all, that gas will be liquefied easily whose molecules have got tendency to come closer, right? And which is that gas whose molecules has got tendency to come closer? That is the gas which has got more value of A, right? More the value of A, more the force of attraction, more the tendency of the molecules to come closer, easily the gas can be liquefied, right? So which gas can be easily liquefied? The one which will have more value of A. The one which will have more value of A. The one which will have more value of A. Okay? Number 2. What about B? Imagine like this. This is one container. This is one more container. Correct? These are the gas molecules. Here, these are the bigger size molecules. So B value is more here, right? B value is less here. When you try to liquefy these gases, liquefaction means you have to bring the molecules closer. Liquefaction means you have to bring the molecules closer. You have to bring the molecules closer, right? When you try to liquefy them, when you bring the molecules closer, since the size of these molecules is more, that means the size of the electron density, the size of the electron cloud of the molecules will be more. And if the size of electron clouds of these molecules is more, when you try to bring them down, can I say there will be more repulsions here, right? If there is more repulsion due to the more size of the electron clouds over here, will the gas be liquefied easily? No, right? So for the gas to be liquefied easily, first of all, A value should be maximum. Force of attraction should be maximum between the molecules. Number 2, size should be minimum. So that when you try to compress them, when you try to liquefy them, there will be less repulsions between their electron clouds. So A should be more and B should be less. So it's option D, right? So it's option D. Is this clear? Is this clear to everyone quickly? Yes? Is this clear to everyone? I hope your van der Waals equation is absolutely clear to everyone. Yeah? Now there comes one more important topic, that is variation. That's variation of compressibility factor. Variation of compressibility factor in different pressure regions. Variation of compressibility factor in different pressure regions. This is again one important topic from which question frequently comes. Let's see what it is all about. First of all, I'm going to plot a graph. The graph which we already plotted long back, I hope you remember that. That was Z versus P curve. I hope you remember. This was your compressibility factor Z and this was pressure of the gas. Correct? And the graph was made at 0 degree centigrade. The graph was made at 0 degree centigrade. And this particular line, it used to represent the ideal gas because the equation of this line was Z is equal to 1, right? Equation of this line was Z is equal to 1. So this particular line, it represents the ideal gas. What about real gases? Real gases do not follow this particular line. For the real gases, the graph used to be like this. For the real gases, the graph used to take a dip in the beginning and it used to go up, right? It used to take a dip in the beginning, then it used to go up. Okay. Now, what exactly I'm going to do? Not all the real gases, I'll say majority of the real gases, they follow this curve, right? Z versus P curve for majority of the real gases will be like this. But for hydrogen and helium, the curve is like this. This is hydrogen, this is helium. Why is it so? You'll get the idea in some time. Why is it so? You'll get the idea in some time, right? This is hydrogen, this is helium. Now, my dear students, let's try to understand this curve properly, okay? So this whole curve over here, I'm going to divide it into three regions. The first region is the smallest one. I'm calling this particular region as very, very low pressure region. Very, very low pressure region, right? From here till here, I'm calling it as, from here to here, I'm calling it as the low pressure region. And after this, I'm calling it as the high pressure region. So what did I exactly do? I divided the curve into three regions. Very, very, very low pressure region, and then high pressure. Okay. Before that, before understanding why I did this, let me just write the van der Waals gas equation. And van der Waals gas equation is P plus AN square divided by V square multiplied by V minus N times B. It's equal to nRT. This is your van der Waals equation. Okay. The real gas for which I made this curve, let's say that real gas is here in this container. Okay, that real gas is here in this container. Imagine that there is 1 mole of real gas in this container. If I want to write the value of Z for this real gas, which is there in the container, Z is equal to PV by nRT, but it has to be PV divided by RT because N value is 1, right? So what I have done, I have taken 1 mole of real gas here in the container. So Z value is equal to PV divided by RT for the real gas. Now, my dear students, when this particular real gas, it's kept at very, very low pressure region, right? This particular real gas, which is kept at 0 degree centigrade, perfect, for which this graph was made, right? This graph is basically made for this particular real gas, whose Z value is this much. When the real gas is kept at very, very, very low pressure region. That means the pressure of this particular real gas is kept very low. So, I'm writing a statement first of all, or before the statement, let me write the same equation for 1 mole of real gas. So it's going to be P plus A by V square. Because N value is 1, I have taken 1 mole of real gas. It's V minus B is equal to RT. This is your van der Waals equation for 1 mole of real gas, correct? Now understand, in this particular equation, we have got two things basically. This particular term and this particular term. This particular term, it gives me the idea about the force of attraction between the molecules, and this particular term, it gives me the idea about the size of the molecules. Now, my dear students, the gas which I have taken in the container, what I'm going to do? I'm going to keep the gas at very, very low pressure. I'm going to keep the gas at very, very low pressure and moderate temperature. The gas which I'm keeping in the container, I'm assuming that the gas is kept at low pressure and moderate temperature. Now, what is going to happen? What's going to happen when the gas is kept at low pressure and moderate temperature? Very, very low pressure and moderate temperature. Very, very low pressure means pressure of this gas is kept very low. So pressure of the gas is approaching towards zero. If pressure of the gas is approaching towards zero, volume will approach towards infinity. If volume will approach towards infinity, that means volume of the container will become infinite. And if volume of the container becomes infinite, the molecules will be at infinite distance apart. And when the molecules are at infinite distance apart, force of attraction between the molecules becomes zero. Since at very, very low pressure, the volume of the container has become infinite. If the volume of the container has become infinite, at that point of time, can I neglect the actual volume of one gas molecule? Absolutely. The actual volume of one gas molecule can be neglected. So, when the gas is kept at very, very low pressure, first, force of attraction between the molecules is zero. If force of attraction between the molecules is zero, that means in this particular equation, that term which is giving me the idea about attractions, that can be neglected. So A by V square, you can neglect it. It gives me the idea about attractions. You can neglect this term at very, very low pressure. And at the same time, since the volume of the container is infinite, so you can neglect the actual volume of one gas molecule. So this particular term, it gives me the idea about the volume. It gives me the idea about the size of the gas molecule, right? You can neglect it as well. Because pressure is very low. Pressure is almost zero. Volume of the container has become infinite. Volume of one gas molecule can be neglected as compared to the whole volume of the container, which is infinite, right? That means the actual volume of one gas molecule, that can be neglected. So at very, very low pressure, you can neglect this term, you can neglect this term. That means instead of P plus A by V square, you can just write P. Instead of V minus B, you can only write what? You can only write V. Now, if I write the same van der Waals equation at very, very low pressure, instead of P plus A by V square, you are writing P. Instead of V minus B, you are writing B. V is equal to RT, right? This is the equation which I wrote at very, very, very low pressure. Okay. Now, dear students, if I divide this equation throughout by RT, divided by RT, PV divided by RT is Z. So Z value for the gas is coming out to be 1. Z value for the gas is coming out to be 1. That means when the real gas is kept at very, very, very low pressure, it behaves like the ideal gas. When the real gas is kept at very, very, very low pressure, it behaves like the ideal gas. That's why the graph starts from here. That's why it starts from Z is equal to 1 line. That's why it starts from Z is equal to 1 line. I hope you're getting it. Okay. Now, from very, very low pressure region, we are going to move into the low pressure region. From very, very low pressure region, we are going to move into low pressure region. So at low pressure, initially the gas was present at very, very low pressure. Now, from very, very low, we are moving to low pressure region and moderate temperature. Okay, and moderate temperature. Now, dear students, initially the gas was present at very, very low pressure region. Now, from very, very low, I'm moving to low pressure region. Does that mean I'm increasing the pressure of the gas? Yes, that means I'm increasing the pressure of the gas. If I'm increasing the pressure of the gas, that means comparatively I'm decreasing the volume of the gas. Slightly I'm decreasing the volume of the gas. Initially, molecules were at infinite distance apart. The molecules have come slightly closer. Distance between them has decreased. Force of attraction has increased. That means at low pressure, Am I going to neglect the force of attraction term? I cannot neglect the force of attraction. But initially, the volume of the container was infinite at very, very low pressure region. Now, from very, very low, you are moving it to low. That means you are increasing the pressure a bit. You are decreasing the volume comparatively. But still, volume is huge only. Still, volume is huge only. Still, you can neglect actual volume of one gas molecule as compared to the whole volume of the container. Right? That means still you can neglect the size of the gas molecule. So, at low pressure, instead of V minus B, you can just write V. Instead of V minus B, you can write V. Now write the equation. The equation is going to be P plus A by V square. P plus A by V square multiplied by V minus B is V is equal to RT. Correct? So multiply throughout. It's going to be PV plus A divided by V is equal to RT. Is equal to RT. Divide throughout by RT. Divided by RT. This is divided by RT. This is divided by RT. Right? Now after dividing by RT, what did I get? Let's get to know what am I going to get over here. See guys, PV divided by RT is basically Z. PV by RT is Z. This is 1 minus A. Z is equal to 1 minus A divided by VRT. This is the value of Z which we got at when the gas is kept at low pressure. When the gas is kept at low pressure. Do you see the value of Z is coming out to be less than 1? Do you see the value of Z is coming out to be less than 1? Just check it out. At low pressure, the value of Z is basically, it is less than 1 only, right? And you saw it mathematically, the value of Z is less than 1. That means which forces are attracting? I mean, which forces are dominating? It's going to be attractive forces which are dominating here. Attractive forces dominate here. Perfect. So this was your low pressure. Now, there is one more region left, which is high pressure. At high pressure and moderate temperature. At high pressure and moderate temperature. You tell me, at high pressure. At high pressure, you tell me which forces are dominating, in short. At high pressure, when you talk about high pressure, the graph is above Z is equal to one line. So repulsive forces are dominating. So at high pressure, if repulsive forces are dominating, so you can neglect the attractive forces. Neglect the attractive forces means instead of P plus A by V square, instead of P plus A divided by V square, you can just write P. That's it. Now write the equation. P plus A by V square, P, multiplied by V minus B is equal to RT. So it is just going to be PV minus PB is equal to RT. Divide throughout by RT. This is RT here. This is RT here. Even this is RT here. Right? So PV divided by RT is Z. Z is equal to 1 plus PB divided by RT. This is one more equation which I would want all of you to remember. And this equation is valid when the gas is kept at high pressure. You check it out. The gas is kept at high pressure. Is the value of Z coming out to be greater than 1? Yes, the value of Z is coming out to be greater than 1. And we know at high pressure, Z value is always greater than 1 only, which you saw mathematically also, right? So this value of Z here is greater than 1. Perfect. The value of Z here is greater than 1. I hope it's clear to everyone. So, and you know if the value of Z is greater than 1, which forces dominate? I would directly say repulsive forces dominate. Repulsive forces dominate. Is this part clear to you? Quickly, is this part clear? All right. I hope this is clear to everyone. Now you must be thinking whether the Z versus P curve for real gas will be always like this. Okay, leave that part aside. Let's first of all talk about the exceptional behavior of hydrogen and helium. Why hydrogen and helium at moderate temperatures, why their Z versus P curve is not like this? Why their Z versus P curve is always greater than 1 only? What is the reason? What is the logic for that? What is the logic for that? So, mark the heading as exceptional behavior for hydrogen and helium. Exceptional behavior of hydrogen and helium. Let's get to know what is the logic behind it. Exceptional behavior of hydrogen and helium. My dear students, hydrogen and helium. Hydrogen and helium. Let me tell you, their molecular mass or atomic mass, right, is negligible basically. The molecular mass is negligible. And you must be knowing, more the molecular mass, more the force of attraction basically. This is one of the general trends. More the molecular mass, more is the force of attraction. Lesser the molecular mass, lesser the force of attraction. Since their molecular mass is negligible, so force of attraction between the molecules, that is negligible. That is negligible. Hydrogen and helium, they're at the top of the periodic table, right? Their molecular mass is negligible. Therefore, force of attraction between them also is negligible. Force of attraction negligible means, that means instead of P plus A by V square, what can I write? I only have to write P, because A by V square is the term which gives me the idea about attractions, so you have to neglect it. Right? If P plus A by V square is P, then write the equation. P plus A by V square is P multiplied by V minus B is equal to RT. So just modify it a bit. So PV minus PB is equal to RT divided by RT, right? This is RT everywhere. So I'll be getting one equation. PV by RT is Z. So Z value is coming out to be 1 plus PB divided by RT. So check the value. Is the value of Z coming out to be greater than 1? Yes, the value of Z is coming out to be greater than 1 only, right? The value of Z will be always greater than 1 for helium and hydrogen. Does that mean always it will be like this? For hydrogen and helium, the curve, the Z versus P curve will be always greater than 1? It depends. It depends. Do remember, at temperature well below minus 60 degrees centigrade. At temperature well below minus 60 degrees centigrade, hydrogen and helium will show the same Z versus P curve as all the other real gases show. Okay? Do remember, at temperature well below minus 60 degrees centigrade, hydrogen and helium will show same curve as other real gases show. Okay? So Z versus P curve for hydrogen and helium can be like this. Right? No worries at all. But you have to keep the temperature of the gas well below minus 60 degrees. Now there must be one more confusion, which maybe you must be thinking, why the graph of hydrogen is at the top and helium is below it? What is the logic behind that? What is the reason behind that? First of all, Z versus P curve for hydrogen. Z versus P equation for hydrogen is this. Z is equal to 1 plus PV by RT. This is the equation for hydrogen helium, right? This is the equation for hydrogen helium. Now, dear students, if you separately plot a graph between Z and P for hydrogen and helium, we know Z is equal to 1 plus PB by RT, right? But I'm going to write 1 plus B divided by RT multiplied by P. This is how I'm going to write it. This is the equation for hydrogen and helium. Now let's plot a graph separately between Z and pressure for hydrogen and helium. So this is Y, this is X. This automatically becomes your M and this becomes your C. So Y is equal to mx plus C. The graph is like this. Separate curve I'm plotting. This is Z, this is P. Y is equal to mx plus C. The graph starts from here, then it's a straight line. Okay. What about the intercept? Intercept means C. That means the distance from here to here is equal to 1 unit. What about the slope of the curve? Slope means M. Slope of the curve is equal to B divided by RT. It's equal to B divided by RT. Basically, one of the curve, these are two curves. One is for hydrogen and one is for helium. Correct? This is the same curve as we have discussed till now. This is Z is equal to one line. This is P and this hydrogen helium. Now let me show you why hydrogen's curve is at the top than that of helium. Dear students, Z versus P curve slope. Z versus P curve slope for hydrogen and helium, that came out to be B divided by RT. That came out to be B divided by RT. So slope over here is directly proportional to B. And B gives us the idea about the size. B gives us the idea about the size. Now we have got two things. One is H2, one is helium. We have got two things. One is molecule, one is atom. One is H2, one is He. One is molecule, one is atom. For molecule, what do we define? For molecule, we define molecular size. So basically, for hydrogen, what do we do? For hydrogen, we define molecular size. And for helium, what do we do? For helium, helium is the atom, we define atomic size. For helium, we define atomic size. For hydrogen, we define molecular size. For helium, what do? We define the atomic size. Okay, we define atomic size. Now you tell me whether molecular size or atomic size, which one is more? Can I say molecular size is more than that of atomic size? So I would say size of H2 is more than that of He. If size of H2 is more, that means B value of H2 has to be more. If B value of H2 is more, that means slope of H2 has to be more. That's why H2 comes at the top. The slope of H2 has more over here. Okay? I hope this point is also clear to you. Right? Let's have a look on one more simple topic which might confuse you afterwards. I'm writing the term compressibility factor. Compressibility factor versus temperature. Compressibility factor versus temperature. Now let's get to know how till now what we were checking. We were checking how compressibility factor changes on changing pressure. Now we are going to check how compressibility factor changes on changing temperature. Okay. For example, I'm making a graph. One simple graph I'm making. See, this is compressibility factor Z and this is pressure P. Z versus P, correct? And over here, I'm going to draw a line. And this line, as you all must be knowing, it represents an ideal gas whose Z value is 1. Okay. Now, for example, I've got a real gas for which I'm making a Z versus P curve. Let's say Z versus P curve for real gas came out to be this when the real gas was at temperature T1. I'm changing the temperature of the real gas from T1 to T2. And at temperature T2, the curve between Z versus P for the real gas at temperature T2 comes like this. At temperature T3, it comes like this. I need to check which temperature is more and which temperature is less. Okay, I have taken a real gas. When the real gas was kept at temperature T1, this is the graph between Z versus P for the real gas. When I change the temperature, the graph got changed. When I change the temperature, the graph got changed. Right? Now we need to check which temperature is more and which temperature is less. My dear students, let's try to do one simple thing over here. This particular point, after this, let's call it as high pressure region, right? And below this, let's call it as low pressure region. Let's call it as low pressure region. So I'm going to analyze this graph in high pressure region as well as low pressure region. Let's see what kind of results do we get. So first of all, if I write over here at high pressure region, tell me at high pressure region whether the value of Z is greater than 1 or less than 1. It's greater than 1. It's 1 plus PB divided by RT. At high pressure region, Z value is 1 plus PB divided by RT, right? Okay. Now, my dear students, when the gas is kept at high pressure, when the real gas is kept at high pressure, this is the equation which real gas will follow, right? So we have got a real gas. Imagine we have got a real gas whose pressure is high. The real gas is kept in a container whose pressure is high. Now I'm going to change the temperature of the real gas. The real gas whose pressure is high, I'm going to change the temperature of that real gas. For example, I'm increasing the temperature of the real gas. If I increase the temperature, this term will decrease. Eventually, this whole term will decrease. That means Z value will decrease. So, when the real gas is kept at high pressure, when you increase the temperature of the real gas, its Z value will decrease. That means Z is inversely proportional to temperature. But at high pressure region, if you increase the temperature of the gas, Z value will decrease. Okay, this is happening at high pressure. Similarly, if I ask you, what will happen at low pressure? If I check the same when the gas is kept at low pressure. Imagine the same real gas is kept at low pressure. Now at low pressure, we are going to change the temperature and see what will happen to its Z value. First of all, at low pressure, you know, the value of Z is less than 1. Z is equal to 1 minus A by VR. A by VRT, right? Now you tell me, if you increase the temperature at low pressure, when the gas is kept at low pressure, when you increase the temperature, this term will decrease. If this term decreases, this whole term will increase. So Z value will increase. So eventually, you got to know Z is directly proportional to T at low pressure. So do remember, at low pressure, Z is directly proportional to temperature. At high pressure, Z is inversely proportional to temperature. Okay, this can be the question asked. Perfect. Do remember this point as well. At low pressure, Z is directly proportional to temperature. At high pressure, Z is inversely proportional to temperature. Now, one question I can give you here. Let me see if you can let me know its correct answer or not. For example, I'm making a question like this: Z versus P. Z versus P graph. And this is, for example, Z is equal to 1 line. This graph is at temperature T1. This is at temperature T2. This is at temperature T3. Now you tell me which temperature is more, which is less, right? Select any of the region. Select either high pressure or low pressure. Let's say we have got high pressure. Draw a straight line. The same procedure. Draw a straight line. Mark these points. After marking these points, get the Z value. Z at temperature T1 is Z1. This will be Z2. This will be Z3. Now tell me which Z is more. Z3 is more than that of Z2, which is more than that of Z1. Okay. At high pressure, Z is inversely proportional to temperature, right? At high pressure, Z is inversely proportional to temperature. More the value of Z, lesser the temperature. So T3 has to be less than T2, which has to be less than T1. This is the correct answer of the question. I hope it is super clear to everyone. Okay. Let me give you one more question. Let me see if we can solve that or not. The question is like this. A non-ideal gas means real gas, okay? A non-ideal gas follows the equation. The equation is P multiplied by V minus B is equal to RT. You can modify the equation. 1 mole of non-ideal gas, okay? 1 mole of non-ideal gas follows this equation. Given that dz upon dP at constant temperature is equal to x times B divided by RT. Calculate the value of x. On simple question this is. It might look complicated to you, but it's not. It's very simple. Okay, it's very simple. The question is, we have got 1 mole of non-ideal gas, which follows this particular equation. Some parameters are given to us. We have to get the value of x. My dear students, it's mentioned that the gas follows the equation. Okay. Now it's given that dz upon dP. That means you are differentiating z with respect to pressure. So my first point will be to convert this particular equation into Z form. If I get this particular equation in the form of Z, then maybe I can differentiate that with respect to P. Okay. So let's try to convert this particular equation into the Z format. The equation is simple. It's P multiplied by V minus B is equal to RT, right? So it's going to be PV minus PB is equal to RT divided throughout by RT. So this is RT here, this is RT here, even this is RT here. So you got to know Z is equal to 1 plus PB divided by RT. So can I say I converted this equation into the Z format? Yes, I did that. Now, dear students, we have to differentiate Z with respect to pressure. So differentiate Z with respect to pressure. So dz upon dP. Keeping what constant? Keeping temperature constant. dz upon dP. So differentiate Z with respect to pressure. So this is constant, its differentiation is 0, right? What about the differentiation of PB by RT? Right? It's going to be B divided by RT because you are differentiating with respect to pressure. You are differentiating with respect to pressure, keeping temperature constant. Now, what did we get? We got to know dz upon dp, dz upon dp, dz upon dp is equal to b by rt, x times b by rt. That means when you compare these two equations, the value of x came out to be what? The value of x came out to be 1. Is this super duper clear to everyone? Can you let me know in the chats? Perfect, guys. Perfecto. One question I'm going to give you as the homework, and with that, we'll end the session. And that was your states of matter chapter, okay? One question I'm giving you as the homework. Calculate the molecular diameter. Calculate the molecular diameter of helium. In angstroms. If B value is equal to 2.4 milliliter per mole. This is your question. Okay, one simple question. And how do we get this particular question? I gave you one result, if you remember, that was B is equal to 4 multiplied by 4 by 3 pi r cube multiplied by Avogadro's number, right? So B value is given to us. We can calculate radius from here. Once we get the radius of the molecule, 2 times radius will give me the diameter of the molecule. Okay, this is your homework question. Give it a try and let me know its answer in the comment section of the video. Okay. So dear students, this was your states of matter chapter. So it's done and dusted. So tomorrow is Sunday, right? So tomorrow I'll be giving you upcoming week's schedule, right? And in the upcoming week, I'm going to increase the frequency of the class a bit. So till now, we used to have only one session every day. But from Monday, we'll have 2 marathons every day, right? Of 4 hours each. Perfect. PDF of this particular session, you'll be getting on t.me/WASSIMSIRCHEM. But I'll send you the PDF of this session in the evening, not now, because I've got one more session. Okay. Do let me know in the comment section of the video. Did you actually like it or not? Okay. So with this, your entire states of matter, with everything, with all the theory, with all the problem patterns, right? That got done and dusted. So next chapter will be most probably redox reactions. We'll finish the redox reactions in 2 sessions. Then similarly, we'll keep on continuing. Okay, in the next week, we'll be completing 2 chapters. Perfect. So let's stop with this. Do let me know in the comment section of the video if you actually liked the session or not. Okay, I'm a bit tired. Hello, see you guys. Take care. God bless you all. Bye.